Hi, my name is Pasan. I'm an instructor at Treehouse, and welcome to the Introduction to Data Structures course. In this course, we're going to answer one fundamental question. Why do we need more data structures than a programming language provides? Before we answer that question, some housekeeping, if you will. In this course, we're going to rely on concepts we learned in the Introduction to Algorithms course, namely big O notation, space and time complexity, and recursion. If you're unfamiliar with those concepts or just need a refresher, check out the prerequisites courses listed. In addition, this course does assume that you have some programming experience. We're going to use data structures that come built into nearly all programming languages as our point of reference. While we will explain the basics of how these structures work, we won't be going over how to use them in practice. If you're looking to learn how to program before digging into this content, check the notes section of this video for helpful links. If you're good to go, then awesome. Let's start with an overview of this course. The first thing we're going to do is to explore a data structure we are somewhat already familiar with, arrays. If you've written code before, there's a high chance you have used an array. In this course, we're going to spend some time understanding how arrays work, what are the common operations on an array, and what are the runtimes associated with those operations. Once we've done that, we're going to build a data type of our own called a linked list. In doing so, we're going to learn that there's more than one way to store data. In fact, there's way more than just one way. We're also going to explore what motivates us to build specific kinds of structures and look at the pros and cons of these structures. We'll do that by exploring 4 common operations: accessing a value, searching for a value, inserting a value, and deleting a value. After that, we're actually going to circle back to algorithms and implement a new one, a sorting algorithm. In the Introductions to Algorithms course, we implemented a binary search algorithm. A precondition to binary search was that the list needed to be sorted. We're going to try our hand at sorting a list and open the door to an entirely new category of algorithms. We're going to implement our sorting algorithm on 2 different data structures and explore how the implementation of one algorithm can differ based on the data structure being used. We'll also look at how the choice of data structure potentially influences the runtime of the algorithm. In learning about sorting, we're also going to encounter another general concept of algorithmic thinking called divide and conquer. Along with recursion, divide and conquer will be a fundamental tool that we will use to solve complex problems. All in due time. In the next video, let's talk about arrays. A common data structure built into nearly every programming language is the array. Arrays are a fundamental data structure and can be used to represent a collection of values, but it is much more than that. Arrays are also used as building blocks to create even more custom data types and structures. In fact, in most programming languages, text is represented using the string type, and under the hood, strings are just a bunch of characters stored in a particular order in an array. Before we go further and dig into arrays, what exactly is a data structure? A data structure is a way of storing data when programming. It's not just a collection of values and the format they're stored in, but the relationship between the values in the collection, as well as the operations applied on the data stored in the structure. An array is one of very many data structures. In general, an array is a data structure that stores a collection of values where each value is referenced using an index or a key. A common analogy for thinking about arrays is as a set of train cars. Each car has a number, and these cars are ordered sequentially. Inside each car, the array, or the train in this analogy, stores some data. While this is the general representation of an array, it can differ slightly from one language to another, but for the most part, all these fundamentals remain the same. In a language like Swift or Java, arrays are homogeneous containers, which means they can only contain values of the same type. If you use an array to store integers in Java, it can only store integers. In other languages, arrays are heterogeneous structures that can store any kind of value. In Python, for example, you can mix numbers and text with no issues. Now, regardless of this nuance, the fundamental concept of an array is the index. This index value is used for every operation on the array, from accessing values to inserting, updating, and deleting. In Python, the language we're going to be using for this course, it's a tiny bit confusing. The type that we generally refer to as an array in most languages is best represented by the list type in Python. Python does have a type called array as well, but it's something different, so we're not going to use it. While Python calls it a list, when we use a list in this course, we'll be talking about concepts that apply to arrays as well in other languages, so definitely don't skip any of this. Now, there's one more thing. In computer science, a list is actually a different data structure than an array. And in fact, we're going to build a list later on in this course. Generally, though, this structure is called a linked list, as opposed to just list, so hopefully the terminology isn't too confusing. To properly understand how arrays work, let's take a peek at how arrays are stored under the hood. An array is a contiguous data structure. This means that the array is stored in blocks of memory that are right beside each other with no gaps. The advantage of doing this is that retrieving values is very easy. In a non-contiguous data structure, and we're going to build one soon, the structure stores a value as well as a reference to where the next value is. To retrieve that next value, the language has to follow that reference, also called a pointer, to the next block of memory. This adds some overhead, which, as you will see, increases the runtime of common operations. A second ago, I mentioned that depending on the language, arrays can either be homogeneous, containing the same type of value, or heterogeneous, where any kind of value can be mixed. This choice also affects the memory layout of the array. For example, in a language like C, Swift, or Java, where arrays are homogeneous, when an array is created, since the kind of value is known to the language compiler, and you can think of the compiler as the brains behind the language, it can choose a contiguous block of memory that fits the array size and values created. If the values were integers, assuming an integer took up space represented by one of these blocks, then for a 5-item array, the compiler can allocate 5 blocks of equally sized memory. In Python, however, this is not the case. We can put any value in a Python list. There's no restriction. The way this works is a combination of contiguous memory and the pointers or references I mentioned earlier. When we create a list in Python, there is no information about what will go into that array, which makes it hard to allocate contiguous memory of the same size. There are several advantages to having contiguous memory. Since the values are stored beside each other, accessing the values happens in almost constant time, so this is a characteristic we want to preserve. The way Python gets around this is by allocating contiguous memory and storing in it not the value we want to store, but a reference or a pointer to the value that's stored somewhere else in memory. By doing this, it can allocate equally sized contiguous memory, since regardless of the value size, the size of the pointer to that value is always going to be equal. This incurs an additional cost in that when a value is accessed, we need to follow the pointer to the block of memory where the value is actually stored, but Python has ways of dealing with these costs that are outside the scope of this course. Now that we know how an array stores its values, let's look at common operations that we execute on an array. Regardless of the kind of data structure you work with, all data structures are expected to carry out 4 kinds of operations at minimum. We need to be able to access and read values stored in the structure. We need to be able to search for an arbitrary value. We also need to be able to insert a value at any point into the structure. And finally, we need to be able to delete structures. Let's look at how these operations are implemented on the array structure in some detail, starting with access. Elements in an array are identified using a value known as an index, and we use this index to access and read the value. Most programming languages follow a zero-based numbering system when it comes to arrays, and all this means is that the first index value is equal to 0, not 1. Generally speaking, when an array is declared, a base amount of contiguous memory is allocated as the array storage. Computers refer to memory through the use of an address, but instead of keeping a reference to all the memory allocated for an array, the array only has to store the address of the first location. Because the memory is contiguous, using the base address, the array can calculate the address of any value by using the index position of that value as an offset. If you want to be more specific, think of it this way. Let's say we want to create an array of integers, and then each integer takes up a certain amount of space in memory that we'll call m. Let's also assume that we know how many elements we're going to create. So the size of the array is some number of elements we'll call n. The total amount of space that we need to allocate is n times the space per item m. If the array keeps track of the location in memory where the first value is held, so let's label that m0, then it has all the information it needs to find any other element in the list. When accessing a value in an array, we use the index. So to get the first element in the list, we use the 0th index. To get the second, we use the index value 1, and so on. Given that the array knows how much storage is needed for each element, it can get the address of any element by starting off with the address for the first element and adding to that the index value times the amount of storage per element. For example, to access the second value, we can start with m0, and to that add m times the index value 1, giving us m1 as the location in memory for the second address. This is a very simplified model, but that's more or less how it works. This is only possible because we know that array memory is contiguous with no gaps.
Let's switch over to some code. As I mentioned earlier, we're going to be using Python in this course. If you don't know how to code, or you're interested in this content but know a language other than Python, check the notes section of this video for more information. While the code will be in Python, the concepts are universal, and more importantly, simple enough that you should have no issue following along in your favorite programming language. Now to get started, click on the Launch Workspaces button on the video page that you're watching right now. This should spin up an instance of a Treehouse workspace, an in-browser coding environment. Right now, your workspace should be empty, and that's expected. So let's add a new file in here. I'm going to go to File, New File, and we'll call this arrays.py. Creating a list in Python is quite simple. So we'll call this new_list. We use a set of square brackets around a set of values to create a list. So 1, and we comma separate them. So space 2 and space 3. This allocates a base amount of memory for the array to use. Or when I say array, know that in Python, I mean a list. Since this is Python, the values aren't stored in memory. Instead, the values 1, 2, and 3 are stored elsewhere in memory, and the array stores references to each of those objects. To access a value, we use a subscript along with an index value. So to get the first value, we use the index 0. And if we were to assign this to another variable, we would say result equal new list. We write out new list since this is the array that we're accessing the value from, and then a subscript notation, which is a square bracket, and then the index value. As we saw, since the array has a reference to the base location in memory, the position of any element can be determined pretty easily. We don't have to iterate over the entire list. All we need to do is a simple calculation of an offset from the base memory, since we're guaranteed that the memory is contiguous. For this reason, access is a constant time operation on an array or a Python list. This is also why an array crashes if you try to access a value using an index that is out of bounds of what the array stores. If you've used an array before, you've undoubtedly run into an error or a crash where you tried to access a value using an index that was larger than the number of elements in the array. Since the array calculates the memory address on the fly, when you access a value with an out-of-bounds index, as it's called, the memory address returned is not one that's part of the array structure and therefore cannot be read by the array. Now in Python, this is represented by an index error, and we can make this happen by using an index we know our array won't contain. Now I'm writing out my code here inside of a text editor, which obviously doesn't run the code. So let's drag up this console area here, and I'm going to write Python to bring up the Python interpreter. And in here, we can do the same thing. So I can say new list equal 1, 2, 3. And now this is an interpreter, so it's actually going to evaluate our code. All right, so now we have a new list. If I type out new list, it gets printed out into the console. Okay, I can also do new list square bracket 0, and you'll see that I get the value 1, which is the value stored at the 0th index. Now, to highlight that index error, we can do new list And inside the square brackets, we can provide an index that we know our array doesn't contain. So here I'll say index 10. And if I hit enter, you'll see it say index error, list index out of range. And those are the basics of how we create and read values from an array. In the next video, let's take a look at searching.
In the last video, we learned what happens under the hood when we create an array and read a value using an index. In this video, we're going to look at how the remaining data structure operations work on arrays. If you took the Introduction to Algorithms course, we spent time learning about two search algorithms, linear search and binary search. While arrays are really fast at accessing values, they're pretty bad at searching. Taking an array as is, the best we can do is use linear search for a worst-case linear runtime. Linear search works by accessing and reading each value in the list until the element in concern is found. If the element we're looking for is at the end of the list, then every single element in the list will have been accessed and compared. Even though accessing and comparing are constant time operations, having to do this for every element results in an overall linear time.
Let's look at how search works in code. In Python, we can search for an item in an array in one of two ways. We can use the in operator to check whether a list contains an item. So I can say if one in new underscore list, then print true. The in operator actually calls a contains method that is defined on the list type, which runs a linear search operation. In addition to this, we can also use a for loop to iterate over the list manually and perform a comparison operation. So I can say for n in new list, if n equals 1, then print true, and then after that, break out of the loop. This is more or less the implementation of linear search. If the array were sorted, however, we could use binary search, but because sort operations incur a cost of their own, languages usually stay away from sorting the list and running binary search, since for smaller arrays, linear search on its own may be faster. Now, again, remember that since this is an editor, this is just a text file, none of these lines of code are evaluated, so you can try that out in here. So we'll copy that. We can come down here and say Python and hit enter. And then when it starts up, we can paste in our list. And now we can try what we just did. So if one in new list, print true. And there you go, it prints true. Now, because we've already learned about linear and binary search in a previous course, there's nothing new going on here. What's more interesting to look at, in my opinion, is inserting and deleting values in an array. Let's start with inserting. In general, most array implementations support three types of insert operations. The first is a true insert, using an index value where we can insert an element anywhere in the list. This operation has a linear runtime. Imagine you wanted to insert an item at the start of the list. When we insert into the first position, what happens to the item that is currently in that spot? Well, it has to move to the next spot at index value 1. What happens to the second item at index position 1? That one moves to the next spot at index position 2. This keeps happening until all elements have been shifted forward one index position. So in the worst case scenario, inserting at the 0th position of an array, every single item in the array has to be shifted forward. And we know that any operation that involves iterating through every single value means a linear runtime. Now, the second way we can insert an item into an array is by appending. Appending, although technically an insert operation, in that it inserts an item into an existing array, doesn't incur the same runtime cost because appends simply add the item to the end of the list. We can simplify and say that this is constant time. This is a constant time operation, but it depends on the language implementation of array. To highlight why that matters, let's consider how lists in Python work. In Python, when we create a list, the list doesn't know anything about the size of the list and how many elements we're going to store. Creating a new empty list like so numbers equal and two empty brackets, So this creates a list and allocates a space of size n plus 1. Since n here is 0, there are no elements in this array, in this list, space is allocated for a one-element list to start off. Because the space allocated for the list and the space used by the list are not the same, what do you think happens when we ask Python for the length of this list? So I can say len numbers. We correctly get 0 back. This means that the list doesn't use the memory allocation as an indicator of its size, because as I mentioned, it has allocated space for a one-element list, but it returns 0, so it determines it in other ways. Okay, so numbers, this list, currently has space for one element. Let's use the append method defined on the type to insert a number at the end of the list. So I can say numbers.append, and I'll pass in 2. Now the memory allocation and the size of the list are the same since the list contains one element. Now what if I were to do something like this? Numbers.append, there needs to be a dot, and I'll add another value, 200. Now since the list only has an allocation for one item at this point, before it can add the new element to the list, it needs to increase the memory allocation and thereby the size of the list. It does this by calling a list resize operation. List resizing is quite interesting because it shows the ingenuity in solving problems like this. Python doesn't resize the list to accommodate just the element we want to add. Instead, in this case, it would allocate 4 blocks of memory to increase the size to a total of 4 contiguous blocks of memory. It does this so that it doesn't have to resize the list every single time we add an element, but at very specific points. The growth pattern of the list type in Python is 0, 4, 8, 16, 25, 35, 46, and so on. This means that as the list size approaches these specific values, resize is called again. If you look at when the size of the list is 4, this means that when appending 4 more values until the size of 8, each of those append operations do not increase the amount of space taken. At specific points, however, when resizing is triggered, space required increases as memory allocation increases. This might signify that the append method has a non-constant space complexity, but it turns out that because some operations don't increase space and others do, when you average all of them out, append operations take constant space. We say that it has an amortized constant space complexity. This also happens with insert operations. If we had a 4-element array, we would have 4 elements and a memory allocation of 4. An insert operation at that point, doesn't matter where it happens on the list, but at that point it would trigger a resize. Inserting is still more expensive though, because after the resize, every element needs to be shifted over 1. The last insert operation that is supported in most languages is the ability to add one list to another. In Python, this is called an extend and looks like this. So I'll say numbers. Now let me actually clear out the console. Oh, actually, well, let's exit Python. We'll clear this out so we're back at the top and we'll start again. So I'll say numbers and we'll set it to an empty list. And now we can say numbers.extend. And as an argument, we're going to pass in a new list entirely. So here we'll say 4, 5, 6. And then once I hit enter, if I were to print out numbers, you'll see that it now contains the values 4, 5, and 6. So extend takes another list to add. Extend effectively makes a series of append calls on each of the elements in the new list until all of them have been appended to the original list. This operation has a runtime of big O of k, where k represents the number of elements in the list that we're adding to our existing list. The last type of operation we need to consider are delete operations. Deletes are similar to inserts in that when a delete operation occurs, the list needs to maintain correct index values. So where an insert shifts every element to the right, a delete operation shifts every element to the left. Just like an insert as well, if we delete the first element in the list, every single element in the list needs to be shifted to the left. Delete operations have an upper bound of big O of n, also known as a linear runtime. Now that we've seen how common operations work on a data structure that we're quite familiar with, let's switch tracks and build our own data structure.
Over the next few videos, we're going to build a data structure that you may have worked with before, a linked list. Before we get into what a linked list is, let's talk about why we build data structures instead of just using the ones that come built into our languages. Each data structure solves a particular problem. We just went over the basics of the array data structure and looked at the cost of common operations that we carry out on arrays. We found that arrays were particularly good at accessing. Reading values happens in constant time. But arrays are pretty bad at inserting and deleting, both of which run in linear time. Linked lists, on the other hand, are somewhat better at this, although there are some caveats, and if we're trying to solve a problem that involves far more inserts and deletes than accessing, a linked list can be a better tool than an array. So what is a linked list? A linked list is a linear data structure where each element in the list is contained in a separate object called a node. A node models two pieces of information, an individual item of the data we want to store, and a reference to the next node in the list. The first node in the linked list is called the head of the list, while the last node is called the tail. The head and the tail nodes are special. The list only maintains a reference to the head, although in some implementations it keeps a reference to the tail as well. This aspect of linked lists is very important, and as you'll see, most of the operations on the list need to be implemented quite differently compared to an array. The opposite of the head, the tail, denotes the end of the list. Every node other than the tail points to the next node in the list, but tail doesn't point to anything. This is basically how we know it's the end of the list. Nodes are what are called self-referential objects. The definition of a node includes a link to another node, and self-referential here means the definition of node includes the node itself. Linked lists often come in two forms: a singly linked list where each node stores a reference to the next node in the list, or a doubly linked list where each node stores a reference to both the node before and after. If an array is a train with a bunch of cars in order, then a linked list is like a treasure hunt. When you start the hunt, you have a piece of paper with the location of the first treasure. You go to that location and you find an item along with a location to the next item of treasure. When you finally find an item that doesn't also include a location, you know that the hunt has ended. Now that we have a high-level view of what a linked list is, let's jump into code and build one together. We'll focus on building a singly linked list for this course. There are advantages to having a doubly linked list, but we don't want to get ahead of ourselves.
Let's start here by creating a new file where we're going to put all our code for our linked list. So we'll call this linked_list.py. And first, we're going to create a class to represent a node. Say class node. Now, node is a simple object in that it won't model much. So first, we'll add a data variable. It's an instance variable here called data, and we'll assign the value none initially. And then we'll add one more. We'll call this next node, and to this we'll assign none as well. So we've created two instance variables, data to hold on to the data that we're storing, and next node to point to the next node in the list. Now we need to add a constructor to make this class easy to create. So we'll add an init method here that takes self and some data to start off. And all we're going to do is assign data to that instance variable we created. So that's all we need to model node. Before we do anything else though, let's document this. So right after the class definition, let's create a doc string. So 3 quotes, next line, and we'll say an object for storing a single node of a linked list. And then on the next line, we'll say it models 2 attributes, data, and the link to the next node in the list. And then we'll close this doc string off with 3 more quotation marks. Okay, using the node class is fairly straightforward. So we can create a new instance of node with some data to store. Now the way we're going to do this is we're going to bring up the console and we're going to type out, like we've been typing out before, Python followed by the name of the script that we wrote, which is linked_list.py. But before we do that, we're going to pass an argument to the Python command. We're going to say dash or hyphen I, and then the name of the script, linked_list.py. So what this does is this is going to run the Python REPL, the read, evaluate, print loop in the console, but it's going to load the contents of our file into that so that we can use it. So I'll hit enter and we have a new instance going. And now we can use the node in here. So we can say n1 equal node. And since we defined that constructor, we can pass it some data. So we'll say 10 here. Now, if we try to inspect this object, the representation returned isn't very useful, which will make things really hard to debug as our code grows. So for example, if I type out n1, you'll see that we have a valid instance here, but it's not very helpful the way it's printed out. So we can customize this by adding a representation of the object using the repr function. Now, in the terminal still, we'll type out exit like that, hit enter to exit the console. And then down here, let's add in some room. Okay, and here we'll say def _repr, another set of double underscores, and then this function takes the argument self. And in here, we can provide a string representation of what we want printed to the console when we inspect that object inside of the console. So here we'll say return. Again, this is a string representation, so inside quotes, we'll say node. So this represents a node instance. And the data it contains, here we'll say %s, which is a Python way of substituting something into a string interpolation. And outside of the string, we can say %again. And here we're saying we want to replace this %s with self.data. Okay, let's hit save. And before we move on, let's verify that this works. So I'm going to come in here, type clear to get rid of everything. And then we'll do what we did again, and you can just hit the up arrow a couple times to get that command. All right, so hit enter. And now, just so you know, every time you run this, you start off, from scratch. So n1 that we created earlier, not there anymore. So let's go ahead and create it. n1 equal node 10. And we can type n1 again and hit enter, and you have a much better representation now. So we can see that we have a node and it contains the data 10. We can also create another one, n2 equal node that contains the data 20. And now we can say n1.nextNode equal n2. So n1 now points to n2. And if we say n1.nextNode, you'll see that it points to that node, the node containing 20. Nodes are the building blocks for a list. And now that we have a node object, we can use it to create a singly linked list. So again, I'm going to exit out of this and then go back to the text editor. And here we'll create a new class. So class linked list. The linked list class is going to define a head. And this attribute models the only node that the list is going to have a reference to. So here we'll say head, and we'll assign none initially. And then like we did earlier, let's create a constructor. So $_init $_. This takes self. And then inside, like before, we'll say self.head equal none. This is the same as doing this, so we can actually get rid of that and just use the constructor. Okay, so again, this head attribute models the only node that the list will have a reference to. Since every node points to the next node, to find a particular node, we can go from one node to the next in a process called list traversal. So in the class constructor here, we've set the default value of head to none so that new lists created are always empty. Again, you'll notice here that I didn't explicitly declare the head attribute at the top of the class definition. And don't worry, that's not an oversight. The self.head in the initializer means that it's still created. Okay, so that's all there is to modeling a linked list. Now we can add methods that make it easier to use this data structure. First, a really simple docstring to provide some information. So here we'll create a docstring, 3 quotation marks, and then we'll say singly linked list, and then close it off. A common operation carried out on data structures is checking whether it contains any data or whether it's empty. At the moment, to check if a list is empty, we would need to query these instance variables, head and so on, every time. Ideally, we would like to not expose the inner workings of our data structure to code that uses it. Instead, let's make this operation more explicit by defining a method. So we'll say def is empty, and this method takes self as an argument, and here we'll say return self.head = none. All we're doing here is checking to see if head is none. If it is, this condition evaluates to true, which indicates the list is empty. Now, before we end this video, let's add one more convenience method to calculate the size of our list. The name convenience method indicates that what this method is doing is not providing any additional functionality that our data structure can't handle right now, but instead making existing functionality easier to use. We could calculate the size of our linked list by traversing it every time using a loop until we hit a tail node, but doing that every time is a hassle. Okay, so we'll call this method size, and as always, it takes self. Unlike calling len on a Python list, not to be confused with a linked list, which is a constant time operation, our size operation is going to run in linear time. The only way we can count how many items we have is to visit each node and call next until we hit the tail node. So we'll start by getting a reference to the head. We'll say current equal self.head. Let's also define a local variable named count with an initial value of 0 that will increment every time we visit a node. Once we hit the tail, count will reflect the size of that list. Next, we'll define a while loop that will keep going until there are no more nodes. So we'll say while current. While current is the same as writing out while current does not equal none, but it's more succinct, so we'll go with this former. If the latter is more precise for you, you can go with that. Now inside this loop, we'll increment the count value, so count plus equal 1. Plus equal, if you haven't encountered it before, is the same as writing count equal count plus 1. So if count is 0 initially, so it's 0 plus 1 is 1, and then we'll assign that back to count. Okay, so count plus equal 1. Next, we're going to assign the next node in the list to current. So current equal current.next node. This way, once we get to the tail and call next node, current will equal none, and the while loop terminates. So at the end, we can return count. As you can see, we need to visit every node to determine the size, meaning our algorithm runs in linear time. So let's document this. Up in our docstring, which we'll add now to size, we'll say returns the number of nodes in the list takes linear time. Let's take a break here. We can now create lists, check if they're empty, and check the size. In the next video, let's start implementing some common operations.
At the moment, we can create an empty list, but nothing else. Let's define a method to add data to our list. Technically speaking, there are 3 ways we can add data to a list. We can add nodes at the head of the list, which means that the most recent node we created will be the head, and the first node we created will be the tail. Or we could flip that around. Most recent nodes are the tail of the list, and the first node to be added is the head. I mentioned that one of the advantages of linked lists over arrays is that inserting data into the list is much more efficient than to the array. This is only true if we're inserting at the head or the tail. Technically speaking, this isn't an insert, and you'll often see this method called add, prepend if the data is added to the head, or append if it's added to the tail. A true insert is where you can insert the data at any point in the list, which is our third way of adding data. We're going to circle back on that. If we wanted to insert at the tail, then the list needs a reference to the tail node. Otherwise, we would have to start at the head and walk down the length of the list, or traverse it, to find the tail. Since our list only keeps a reference to the head, we're going to add new items at the head of the list.
Now, before we add our new method, I forgot that I didn't show you in the last video how to actually use the code we just added and how to check every time, when we add new code that it works correctly. So like before, we're going to bring up the console, and here we're going to say python-i linked_list.py, which should load the contents of our file. And now we'll start here by creating a linked list. So L equal linked list. And then we'll use a node. So N1 equal node with the value 10. And now we can assign N1 to the nodes or to the linked list's head attribute. So L1.head equal N1. And then we can see if size works correctly. So if we call L1.size, and since this is a method, we need a set of parentheses at the end, and enter, you'll see that we get back 1 correctly. Okay, so it works. Now, let's add our new method, which we're going to call add. Add is going to accept some data to add to the list inside of a node. So we'll say def add, and every Python method takes self as an argument, and then we want to add some data to this node, so we're going to say data for the second argument. Inside the method, first we'll create a new node to hold on to the data. So new_node equal node with the data. Before we set the new node as the head of the list, we need to point the new node's next property at whatever node is currently at head. This way, when we set the new node as the head of the list, we don't lose a reference to the old head. So new_node.nextNode equal self.head. Now, if there was no node at head, this correctly sets next node to none. Now we can set the new node as the head of the node. So say self.head equal new_node. Because the insert operation is simply a reassignment of the head and next node properties, this is a constant time operation. So let's add that in as a docstring. First, what the method does. So it adds a new node containing data at the head of the list. This operation takes constant time, which is our best case scenario. Okay, let's test this out. So I'm going to bring the console back up. We'll exit out of our current REPL, and we'll load the contents of the file again. And now we don't need to create a node like we did earlier. So we can say L equal linked list, L.add1. Okay, let's see if this works. We'll call size. And if it worked, the linked list should now have a size of 1. There we go. You can also do L.add2, L.add3, and L.size should now be 3. There we go. Now, if I were to type L and just hit print, again, what we get in the REPL is nothing useful. So like before, we'll implement the repr function for our linked list. Now, I'm just going to copy paste this in and we'll walk through it. Okay, so this is what our implementation of repr looks like for the linked list object. You can grab this code from the notes section of this video. Okay, so at the top, you'll see a docstring where it says it returns a string representation of the list. And like everything we need to do with a linked list, we need to traverse it. So this is going to take linear time. We start by creating an empty list. Now, I need to distinguish this is a Python list, not a linked list. So we create an empty list called nodes. And to nodes, we're going to add strings that have a description, that provide a description of each node. But we're not going to use the description that we implemented in the node class because we're going to customize it a bit here. Next, we start by assigning self.head to current. So we sort of have a pointer to the head node. As long as current does not equal none, which means we're not at the tail, we're going to implement some logic. So in the first scenario, if the node assigned to current is the same as the head, then we're going to append this string to our nodes list. And this string is simply going to say that, hey, this is a head node, and it contains some data, which we'll extract using current.data. Next scenario is if the node assigned to current's next node is none, meaning we're at the tail node, then we'll assign a different kind of string. So it's the same as earlier, except we're saying tail here. And then finally, in any other scenario, which means we're not at the head or not at the tail, we'll simply print the node's value inside And again, we'll extract it using current.data. With every iteration of the loop, we'll move current forward by calling current.nextNode and reassigning it. And then at the very end, when we're done, we'll join all the strings that are inside the nodes list together using the Python join method. And we'll say that with every join, so when you join these two strings together to make one string, you need to put this set of characters in between. All right, so let's see what this looks like. So I'm going to come down here, exit out of the console again, clear it out, load the contents of the file again, and let's try that. So we'll say L equal linked list. All right, so L.add1, L.add2, L.add3. That seems enough. And then now if I type out L and hit enter, we get a nice string representation of the list. So you can see that we add every new node to the head. So we added 1 first. 1 ends up being the tail because it keeps getting pushed out. Then 2, and then finally 3. So 3 is at the head. So far, we've only implemented a single method, which functions much like the append method on a Python list or an array, except it adds it to the start of the linked list. It prepends it. Like append, this happens in constant time. In the next video, let's add the ability to search through our list. For the search operation, we're going to define a method that takes a value to search for and returns either the node containing the value, if the value is found, or none if it isn't. So right after, actually, you know what? We'll make sure repr is the last function or last method in our class. So we'll add it above it. So here we'll say def search self and then key. In the last video, we implemented the repr method to provide a string representation of the list. So we're going to use similar logic here to implement the search function. We'll start by setting a local variable current to point to the head of the list. While the value assigned to current is a valid node, that is, it isn't none, we'll check if the data on that node matches the key that we're searching for. So while current, we'll say if current.data is the key, then we'll return current. If it does match, we'll go ahead and return it like we've done here. But if it doesn't, we'll assign the next node in the list to current and check again. So we'll say else current equal current.nextNode. Once we hit the tail node and haven't found the key, current gets set to none and the while loop exits. At this point, we know the list doesn't contain the key, so we can return none. Okay, that completes the body of our method. Let's add a doc string to document this. So up at the top, we'll say search for the first node containing data that matches the key. Now this is important because if our linked list contains more than one node with the same value, it doesn't matter. We're going to return the first one with this implementation. We'll also say here that it returns the node or none if not found. In the worst case scenario, we'll need to check every single node in the list before we find the key or fail. And as a result, this operation runs in linear time. So we'll say takes O of n or linear time. So far, we haven't seen anything that indicates this data structure has any advantage over an array or a Python list, but we knew that. I mentioned the strength of linked lists comes in inserts and deletes at specific positions. We'll check that out in the next video, but as always, before we end this one, let's make sure everything works. So we'll load the contents of the file again. L equal linked list. And then we'll say L.add 10, L.add 20, 2 doesn't matter, L.add 45, and one more, L.add 15. Now we can say L.search, and we need to give it a value, so we'll say 45, and this returns a node or none, so we'll say n equal, and then we'll hit enter. If this works, n should be a node. Okay, weirdly, n does not work here. at least it says it's not a node, which means I made a mistake in typing out our code. And looking at it immediately, it's fairly obvious. So this return none needs to be outside of the while loop. Okay, so I'm going to hit save now. So make sure it's on the same indentation here, which means it's outside the while loop. And then we'll run through this again. Okay, so L is linked list. L.add 10, L.add 2, L.add 45. And what was the last one we did? I believe it was 15. And now we should be able to say L.search. Remember, we're assigning this to a node, to a variable. So L.search 45. And there you go. We get that node back, and we can hit L, and we'll see a representation of our list. Okay, so again, in the next video, inserts and deletes at specific positions.
Insert operations on linked lists are quite interesting. Unlike arrays, where when you insert an element into the array, all elements after the particular index need to be shifted, with a linked list, we just need to change the references to next on a few nodes, and we're good to go. Since each node points to the next one, by swapping out these references, we can insert a node at any point in the list in constant time. Much like binary search though, there's a catch. To find the node at that position we want to insert, we need to traverse the list and get to that point. We just implemented our search algorithm for the linked list type, and we know that this runs in linear time. So while actually inserting is fast, finding the position in the list you want to insert it is not. This is why I mentioned that there were some caveats to inserting. Anyway, let's see what this looks like in code.
We'll define a method named insert that takes data to insert along with an index position. So we'll do this after search right here. Say def insert. And this takes some data to insert and a position to insert it at. You might be thinking, wait a minute, linked lists don't have index positions, right? And you're correct, but we can mimic that behavior by just counting the number of times we access next node. If the index value passed into this argument is 0, that means we want to insert the new node at the head of the list. This is effectively the same behavior as calling add, which means the logic is the same, so we don't need to repeat it. We can call the add method we wrote earlier. So we'll say if index equals 0, or if index is 0, then self.add data. If the index is greater than 0, then we need to traverse the list to find the current node at that index. So if index is greater than 0, now before we do that, we need to create a new node containing the data we want to insert. So we'll say new equal node with some data. I'm going to assign index, the argument passed to our function, to a local variable named position, and the head of the list to a variable named current. Position equal index, current equal self.head. Every time we call current.nextNode, meaning we're moving to the next node in the list, we'll decrease the value of position by 1. When position is 0, we'll have arrived at the node that's currently at the position we want to insert in. In reality, though, we don't want to decrease it all the way to 0. Imagine we have a list with 5 nodes, and we want to insert a node at position 3. To insert a node at position 3, we need to modify the nodes at positions 2 and 3. Node 2's next node attribute is going to point to the new node, and the new node's next node attribute will point to node 3. In this way, an insert is a constant time operation. We don't need to shift every single element, we just modify a few next node references. In a doubly linked list, we can use node 3 to carry out both of these operations. Node 3 in a doubly linked list would have a reference to node 2, and we can use this reference to modify all the unnecessary links. And a singly linked list, though, which is what we have, if we kept decreasing position until we're at 0, we arrive at node 3. We can then set the new node's next node property to point to node 3, but we have no way of getting a reference to node 2, which we also need. For this reason, it's easier to decrease position to just 1 when it equals 1 and stop at node 2. So in here, we'll say while position is greater than 1. Now, while the position is greater than 1, we'll keep calling next node and reassigning the current node. So current equal node.next node. And at the same time, we'll decrement position. So position equal to position minus 1, which you can also succinctly write as minus equal 1. This way, when the position equals 1, the loop exits and current will refer to the node at the position before the insert point. So outside the while loop, we'll say previous equal current and next equal current.next node. To make things more clear, what I've done here is name the node before the new one previous and the node after the new one next. All that's left to do now is to insert the new node between previous and next. So we'll say previous.next node equal new, and then new.next node equal next. Now it seems like there's an issue with variable naming here, and I'm most probably conflicting with some globally named next variable. So we'll actually go ahead and call this next node and previous node so that we don't mess things up here. Previous node. So the .next node is obviously the attribute on a node, but this is just a local variable. Let's document this method. So up at the top, we'll add a docstring, and here we'll say inserts a new node containing data at index position. Insertion takes constant time, but finding the node at the insertion point takes linear time. Let's add this to the next line. There we go. And then we'll say, therefore, it takes an overall linear time. This is why, even though we can easily insert a new node without having to shift the rest, ultimately adding to either the head or the tail, if you have a reference, is much more efficient. We have one more operation to add to our linked list that will make it a robust data structure.
Much like inserts, removing a node is actually quite fast and occurs in constant time. But to actually get to the node that we want to remove and modify the next connections, we need to traverse the entire list in our worst case. So in the worst case, this takes linear time. Let's add this operation to our data structure.
There are two ways we can define the remove method. One where we provide a key to remove as an argument, and one where we provide an index. Now in the former, the key refers to the data the node stores. So in order to remove that node, we would first need to search for data that matches the key. I'm going to implement that first method, which we'll call remove, and I'll leave it up to you to get some practice in and implement a remove at index method to complete our data structure. So we'll add this after the insert method right here. Remove is going to accept a key, which we'll need to search for before we can remove a node. Earlier, we defined a search method that found a node containing data that matches a key, but we can't use that method as is for the implementation of remove. When we remove a node, much like the insert operation, we need to modify the next node references. The node before the match needs to point to the node after the match. If we use the search method we defined earlier, we get the node we want to remove as a return value, but because this is a singly linked list, we can't obtain a reference to the previous node. Like I said earlier, if this was a doubly linked list, we could use the search method since we would have a reference to that previous node. We'll start here by setting a local variable named current to point to the head. Let's also define a variable named previous that we'll set to none to keep track of the previous node as we traverse the list. Finally, let's declare a variable named found that we'll set to false. Found is going to serve as a stopping condition for the loop that we'll define. We'll use the loop to keep traversing the linked list as long as found is false, meaning we haven't found the key that we're looking for. Once we found it, we'll set found to true and the loop terminates. So let's set up our loop. So we'll say while current and not found. Here we're defining a while loop that contains two conditions. First, we tell the loop to keep iterating as long as current does not equal none. When current equals none, this means we've gone past the tail node and the key doesn't exist. The second condition asks the loop to keep evaluating as long as not found equals true. Now this might be tricky because it involves a negation here. Right now found is set to false. So not found, not false, equals true. This not operator flips the value. When we find the key and we set found to true, not found, will equal false then, and the loop will stop. The and in the while loop means that both conditions, current being a valid node and not found equaling true, both have to be true. If either one of them evaluates to false, then the loop will terminate. Now inside the loop, there are three situations that we can run into. First, the key matches the current node's data and current is still at the head of the list. This is a special case because the head doesn't have a previous node and it's the only node being referenced by the list. Let's handle this case. So we'll say if current.data double equals the key and current is self.head, which you can write out as current equals self.head or current is self.head. Now, if we hit this case, we'll indicate that we found the key by setting found to true. And then this means that on the next pass, this is going to evaluate to false because not true will be false. And then the loop terminates. Once we do that, we want to remove the current node. And since it's the head node, all we need to do is point head to the second node in the list, which we can get by referencing the next node attribute on current. Self.head equal current.nextNode. So when we do this, there's nothing pointing to that first node, so it's automatically removed. The next scenario is when the key matches data in the node, and it's a node that's not the head. So here we'll say else if current.data equal key. If the current node contains the key we're looking for, we need to remove it. To remove the current node, we need to go to the previous node and modify its next node reference to point to the node after current. But first, we'll set found to true, and then we'll switch out the references. So previous.nextNode equal current.nextNode. So far, we haven't written any code to keep track of the previous node. We'll do that in our else case here. So if we hit the else case, it means that the current node we're evaluating doesn't contain the data that matches the key. So in this case, we'll make previous point to the current node and then set current to the next node. So previous equal current and current equal current.nextNode. And that's it for the implementation of remove. Now, we're not doing anything at the moment with the node we're removing, but it's common for remove operations to return the value being removed. So at the bottom, outside the while loop, let's return current. And with that, we have a minimal implementation of a linked list and your first custom data structure. How cool is that? There's quite a bit we can do here to improve our data structure, particularly in making it easy to use. But this is a good place to stop. Before we move on to the next topic, let's document our method. So at the top, another docstring, and here we'll say removes node containing data that matches the key. Also, it returns the node or none if the key doesn't exist. And finally, this takes linear time because in the worst case scenario, we need to search the entire list. If you'd like to get in some additional practice implementing functionality for linked lists, two methods you can work on are remove at index and node at index to allow you to easily delete or read values in a list at a given index. Now that we have a linked list, let's talk about where you can use them. The honest answer is not a lot of places. Linked lists are really useful structures to build for learning purposes because they're relatively simple and are a good place to start to introduce the kinds of operations we need to implement for various data structures. It is quite rare, however, that you will need to implement a linked list on your own. There are typically much better, and by that I mean much more efficient data structures that you can use. In addition, many languages, like Java for example, provide an implementation of a linked list already. Now that we have a custom data structure, let's do something with it. Let's combine the knowledge we have and look at how a sorting algorithm can be implemented across two different data structures.
Now that we've seen two different data structures, let's circle back and apply what we know about algorithms to these new concepts. One of the first algorithms you learned about was binary search. And we learned that with binary search, there was one precondition. The data collection needs to be sorted. Over the next few videos, let's implement the merge sort algorithm, which is one of many sorting algorithms on both arrays, or Python lists, and the singly linked list we just created. This way, we can learn a new sorting algorithm that has real-world use cases and see how a single algorithm can be implemented on different data structures. Before we get into code, let's take a look at how merge sort works conceptually, and we'll use an array to work through this. We start with an unsorted array of integers, and our goal is to end up with an array sorted in ascending order. Merge sort works, like binary sort, by splitting up the problem into subproblems, but it takes the process one step further. On the first pass, we're going to split the array into two smaller arrays. Now in binary search, one of these subarrays would be discarded, but that's not what happens here. On the second pass, we're going to split each of those subarrays into further, smaller, evenly sized arrays. And we're going to keep doing this until we're down to single element arrays. After that, the merge sort algorithm works backwards, repeatedly merging these single element arrays and sorting them at the same time. Since we start at the bottom, by merging two single element arrays, we only need to make a single comparison to sort the resulting merged array. By starting with smaller arrays that are sorted as they grow, merge sort has to execute fewer sort operations than if it sorted the entire array at once. Solving a problem like this by recursively breaking down the problem into subparts until it is easily solved is an algorithmic strategy known as divide and conquer. But instead of talking about all of this in the abstract, let's dive into the code. This way, we can analyze the runtime as we implement it.
For our first implementation of merge sort, we're going to use an array or a Python list. While the implementation won't be different conceptually for a linked list, we will have to write more code because of list traversal and how nodes are arranged. So once we have these concepts squared away, we'll come back to that. Let's add a new file here. We'll call this merge_sort.py. In our file, let's create a new function named merge sort that takes a list. And remember, when I say list, unless I specify linked list, I mean a Python list, which is the equivalent of an array. So we'll say def merge_sort and takes a list. In the Introduction to Algorithms course, we started our study of each algorithm by defining the specific steps that comprise the algorithm. Let's write that out as a docstring, in here, the steps of the algorithm, so that we can refer to it right in our code. This algorithm is going to sort the given list in an ascending order. So we'll start by putting that in here as a simple definition. Sorts a list in ascending order. There are many variations of merge sort, and in the one we're going to implement, we'll create and return a new sorted list. Other implementations will sort the list we pass in, and this is less typical, in an operation known as sort in place. But I think that returning a new list makes it easier to understand the code. Now these choices do have implications though, and we'll talk about them as we write this code. For our next bit of the docstring, let's write down the output of this algorithm. So returns a new sorted list. Merge sort has three main steps. The first is the divide step, where we find the midpoint of the list. So we'll say divide, find the midpoint of the list and divide into sublists. The second step is the conquer step, where we sort the sublists that we created in the divide step. So we'll say recursively sort the sublists created in previous step. And finally, the combine step, where we merge these recursively sorted sublists back into a single list. So merge the sorted sublists created in previous step. When we learned about algorithms, we learned that a recursive function has a basic pattern. First, we start with a base case that includes a stopping condition. After that, we have some logic that breaks down the problem and recursively calls itself. Our stopping condition is our end goal, a sorted array. Now, to come up with a stopping condition or a base case, we need to come up with the simplest condition that satisfies this end result. So there are two possible values that fit, a single element list or an empty list. Now, in both of these situations, we don't have any work to do. If we give the merge sort function an empty list or a list with one element, it's technically already sorted. We call this naively sorting. So let's add that as our stopping condition. We'll say if len list, if the length of the list is less than or equal to 1, then we can return the list. Okay, so this is our stopping condition. And now that we have a stopping condition, we can proceed with the list of steps. First, we need to divide the list into sublists. To make our functions easier to understand, we're going to put our logic in a couple different functions instead of one large one. So I'll say left half, comma right half, equal split list. So here we're calling a split function that splits the list we pass in and returns two lists split at the midpoint. Because we're returning two lists, we can capture them in two variables. Now, you should know that this split function is not something that comes built into Python. This is a global function that we're about to write. Next is the conquer step, where we sort each sublist and return a new sorted sublist. So we'll say left equal merge sort left half, and right equal merge sort right half. This is the recursive portion of our function. So here we're calling merge sort on this divided sublist. So we divide the list into two here, and then we call merge sort on it again. This further splits that sublist into two. In the next pass through of merge sort, this is going to be called again and again and again until we reach our stopping condition, where we have single element lists or empty lists. When we've subdivided until we cannot divide anymore, then we'll end up with a left and a right half, and we can start merging backwards. So we'll say return merge left and right. That brings us to the combine step. Once two sublists are sorted and combined, we can return it. Now, obviously, none of these functions, merge sort is written, but merge and split haven't been written. So all we're going to do here if we run it is raise an error. So in the next video, let's implement the split operation.
The first bit of logic we're going to write is the divide step of the algorithm. This step is fairly straightforward and only requires a few lines of code, but is essential to get the sorting process going.
All right, so as we saw earlier, we're going to call the function for the divide step split. So we'll say def split, and split is going to take as an argument a list to split up. Let's document how this function works. So we'll say divide the unsorted list at midpoint into sublists. And it's always good to say what we're returning as well. So we'll say returns two sublists, left and right. All right, so the first step is to determine the midpoint of this list, of this array. We're going to use the floor division operator for this. Floor division carries out a division operation, and if we get a non-integer value like 2.5 back, it just gets rounded down to 2. We'll define the midpoint to be the length of the list divided by 2 and then rounded down. So len list, and using the 2 forward slashes for the floor division operator, we'll put number 2 after it. Okay, once we have the midpoint, we can use the slicing notation in Python to extract portions of the list we want to return. For instance, we can define left as the left sublist that goes all the way from the start of the list all the way up to the midpoint without including the midpoint. Now over here, we're using the slicing syntax where it's like using the subscript notation to access a value from a list, but instead we give 2 index values as a start and stop. If we don't include a start value, as I've done here, Python interprets that as starting from the 0th index or the start of the list. Now similarly, we can define right to be values on the right of the midpoint, so starting at the midpoint and going all the way up to the end of the list. So a couple things to note. As I said earlier, when you don't include the starting index, it interprets it as to start at the very beginning of the list. The index you give as the stopping condition, that value is not included in the slice. So over here, we're starting at the very beginning of list, and we go all the way up to midpoint, but not including midpoint. And then right starts at midpoint, so it includes that value, and then goes all the way to the end of the list. Now, once we have these 2 sublists, we can return them. So we'll return left and right. Notice that we're returning 2 values here. And then in the merge sort function, when we call that split function, we're declaring 2 variables, left half and right half, to assign so that we can assign these 2 sublists to them. Okay? And that's all there is to the split function. In the next video, let's implement the crucial portion of the merge sort logic.
Once we run the split function recursively over the array, we should end up with several single member or empty arrays. At this point, we need to merge them all back and sort them in the process, which is what our merge function is for.
The merge function is going to take 2 arrays or lists as arguments, and to match the naming conventions we used in the split function, we'll call this left and right as well. So we'll say def merge takes a left and a right list. Now, like before, let's add some documentation to our function. So this function merges 2 lists or arrays, sorting them in the process. And then it returns a new merged list. Since our function is going to return a new list, let's start by creating one. Now, in the process of merging, we need to sort the values in both lists. To sort, we need to compare values from each array or each list. So next, let's create 2 local variables to keep track of index values that we're using for each list. So the convention here is I and j, so we'll stick to it. So I equals 0, j equals 0. As we inspect each value in either list, we'll use the variables to keep track of the indexes of those values. So we'll use I to keep track of indexes in the left list and j for indexes in the right list. When merging, we want to keep sorting the values until we've worked through both lists. So for our loop, let's set up 2 conditions with an AND operator. So we'll say while, let's just stay up here, while I is less than the length of the left list and j is less than the length of the right list, then we'll keep executing our loop. So here we're ensuring that as long as I is less than the length of the left list, and the AND is important, and j is less than the length of the right list, we're going to keep executing the code. Now I and j are both set to 0 initially, which means that our first comparison operation will be on the first element of each list respectively. So we'll say if left I, so I is 0, so this is going to get the first value out of the left list, is less than right j, and again here, j is 0, so we're going to get the first value out of the right list. Now, if the value at index I in the left list is less than the value at index j in the right list, what do? Well, that means the value being compared in left is less than the value in the right and can be placed at position 0 in the new array L that we created earlier. So here we'll say L.append left I. Since we've read and done something with the value at position I, let's increment that value so we move forward to evaluate the next item in the left list. I plus 1, or we can say I plus equal 1. Okay, next is an else statement. And here we'll say, if the value at index I, so I don't have to write out the actual logic because it's implied. So here we're saying that left, the value at left is less than the value at right. Now in the else clause, if the value at, so I equal is greater, and I haven't written out that condition because it's implied. So here we're saying if the value in the left is less than the value in the right. So in the else clause, it's going to mean that the value in the left is either greater than or equal to the value in the right. But when we hit the else clause, if the value at index I in the left list is greater, then we place the value at index j from the right list at the start of the new one, list L, and similarly increment j. So here we'll say L.append right j, and then j equal j plus 1. Doing this doesn't necessarily mean that in one step we'll have a completely sorted array, but remember that because we start with single element arrays and combine with each merge step, we will eventually sort all the values more than one time. And by the time the entire process is done, all the values are correctly sorted. Now, this isn't all we need to do in the merge step, however. There are two situations we can run into. One where the left array is larger than the right and vice versa. So this can occur when an array containing an odd number of elements needs to be split. So how do you split a 3-element array or list? Well, the left can have 2 elements and the right can have 1, or the other way around. In either case, our while loop uses an AND condition where the variables used to store the indexes need to be less than the length of the lists. If the left list is shorter than the right, then the first condition returns false and the entire loop returns false because it's an AND condition. This means that in such an event, when the while loop terminates, not all the values in the right list will have been moved over to the new combined list. So to account for this, let's add 2 more while loops. The first while loop is going to account for a situation where the right list is shorter than the left, and the previous loop terminated because we reached the end of the right list first. So in this case, what we're going to do is simply add the remaining elements in the left to the new list. We're not going to compare elements because we're going to assume that within a list, the elements are already sorted. So while I is less than length of left, then it's the same logic. L.append left I, and I plus equal 1. So the while loop is going to have the similar condition. Keep the loop going until it's at the last index. Inside the body, we're incrementing the index with every iteration of the loop. Our final loop accounts for the opposite scenario, where the left was shorter than the right. The only difference here is that we're going to use the variable j along with the right list. So we'll say while j is less than length of right, L.append right j, and j plus equal 1. Okay, let's stop here. In the next video, let's test out merge sort, make sure our code is running correctly and everything's written well, and then we'll wrap up this stage by documenting our code and evaluating the runtime of our algorithm. In the last video, we completed our implementation for the merge sort algorithm, but we didn't test it in any way. Let's define a new list at the bottom that contains several numbers. You can put whatever you want in there, but make sure that the numbers are not in order. I'll call mine a list. And in here, we'll say 54, 26, or 62, doesn't matter, 93, 17, 77, 31. Just add enough so that you can make out that it's sorted. Okay, next we're going to call the merge sort algorithm and pass in our list. Let's assign this to some variable. So we'll say L equal merge underscore sort a list. And then if it works correctly, we should be able to print this list and see what it looks like. So I'm going to hit save. Down here in the console, we'll type out Python merge sort.py. And before I hit enter, I actually noticed I made an error in the last video, but I'll hit enter anyway, and you should see the error pop up. Okay, so what I forgot to do, which is a pretty crucial part of our algorithm, is in the merge function, I forgot to return the list containing the sorted numbers after carrying out all this logic. So here at the bottom, we'll say return L. All right, we'll save again. And now we'll clear this out and try that one more time. And there we go. You should see a sorted list printed out. We can write out a more robust function to test this because with bigger arrays, visually evaluating that printed list won't always be feasible. So we'll bring this back down. Let's get rid of this. And we'll call our function verify sorted. And this will take a list. First, we're going to check inside the body of the function, we'll check the length of the list. If the list is a single element list or an empty list, we don't need to do any unnecessary work because remember, it is naively sorted. So we'll say if n equals 0 or if n equals 1, then we'll return true. We verified that it's sorted. Now to conclude our function, we're going to write out one line of code that will actually do quite a bit of work. So first we'll say return list 0. So we'll take the first element out of the list and we'll compare and see if that's less than the second element in the list. Okay, so first we'll check that the first element in the list is less than the second element in the list. This returns either true or false, so we can return that directly. But this isn't sufficient. If it were, we could trick the verify function by only sorting the first two elements in the list. So to this return statement, we're going to use an AND operator to add on one more condition. For this condition, we're going to make a recursive function call back to verify sorted. And for the argument, we're going to pass in the list going from the second element all the way to the end. Let's visualize how this would work. We'll use a 5-element list as an example. So we'll call verify sorted and pass in the entire list. This list is not 1 or 0 elements long, so we skip that first if statement. There's only one line of code left in the function. And first we check that the element at index 0 is less than the element at index 1. If this is false, the function returns immediately with a false value. An AND operator requires both conditions to be true for the entire line of code to return true. Since the first condition evaluates to false, we don't need to bother evaluating the second. The second condition is a recursive call with a sublist containing elements from the original list starting at position 1 and going to the end. So on the second call, again, we can skip that first if statement and proceed to check whether the value at element 0 is less than the value at element 1. Remember that because this list is a sublist of the original, starting at the element that was the second element in the original list, by comparing the elements at position 0 and 1 in the sublist, we're effectively comparing the elements at position 1 and 2 in the original list. With each recursive call, as we create new sublists that start at index position 1, we're able to check the entire list without having to specify any checks other than the first two elements. Since this is a recursive function, it means we need a stopping condition, and we have it already. It's that first if condition. As we keep making sublists, once we reach a single element list, that element is already sorted by definition, so we can return true. Since this recursive function call is part of an AND condition, it means that every single recursive call has to return true all the way back to the beginning for our top level function to return true and for the function to say, yes, this is sorted. Now, we could have easily done this using an iterative solution and a for loop, but this way, you get another example of recursion to work through and understand. So let's use this function. At the bottom, we'll say print verify sorted, and first we'll pass in a list. Oops, we got rid of that, didn't we? Okay, let me write it out again. So a list equal, and I think I have those original numbers here somewhere. So we'll say 54, 26, 93, Okay, and then we assign to L the result of calling merge sort on a list. Okay, so now here we're going to use the verify sorted function, and we'll check first that a list is sorted. That should return false. And then we'll check the same call on, and we'll pass an L, and this should return true. Okay, so now at the bottom here in the console, we'll call Python merge sort.py, and there we go. It returned false for a list, meaning it's not sorted, but L is sorted. Cool. So our merge sort function works. In the next video, let's talk about the cost of this algorithm. If we go back to the top level, the merge sort function, what does the runtime of this function look like, and what about space complexity? How does memory usage grow as the algorithm runs? To answer those questions, let's look at the individual steps, starting with the split function. In the split function, all we're doing is finding the midpoint of the list and splitting the list at the midpoint. This seems like a constant time operation, but remember that the split function isn't called once. It's called as many times as we need it to go from the initial list down to a single element list. Now, this is a pattern we've seen a couple times now, and we know that overall, this runs in logarithmic time. So let's add that as a comment. So here I'll say, takes overall big O of log n time. Now, there's a caveat here, but we'll come back to that. So next up is the merge step. In the merge step, we've broken the original list down into single element lists, and now we need to make comparison operations and merge them back in the reverse order. For a list of size n, we will always need to make an n number of merge operations to get back from single element lists to a merge list. This makes our overall runtime big O of n times log n, because that's an n number of merge steps multiplied by a log n number of splits of the original list. So to our merge step here, let's add a comment. We'll say it runs in overall, runs in overall linear time, right? It takes an n number of steps, number of merge steps. But now that we have these two, so linear here and logarithmic here, we can multiply these and say that the merge sort function, the top level function, we can conclude that the runtime of the overall sorting process is big O of n times log n. Now, what about that caveat I mentioned earlier? So if we go back to our split function here, right here, there we go. Let's take a look at the way we're actually splitting the list. So we're using Python's list slicing operation here and passing in two indexes where the split occurs. Now, if you go and poke around the Python documentation, which I've done, it says that a slicing operation is not a constant time operation, and in fact has a runtime of big O of k, where k represents the slice size. This means that in reality, our implementation of split, this implementation of split, does not run in logarithmic time, but k times logarithmic time, because there's a slice operation for each split. This means that our implementation is much more expensive. So overall, that makes our overall top-level merge sort function not n times log n, but kn times log n, which is much more expensive. Now, let's get rid of all that. To fix this, we would need to remove this slicing operation. Now, we can do that by using a technique we learned in a previous course. In the Introduction to Algorithms course, we looked at two versions of binary search in Python, a recursive and an iterative version. In the recursive one, we use list slicing with every recursion call, but we achieve the same end result using an iterative approach without using list slicing. Over there, we declared two variables to keep track of the starting and ending positions in the list. We could rewrite merge sort to do the same, but I'll leave that as an exercise for you. If you want some hints, or if you want any direction, I've included a link in the notes with an implementation. So that is time complexity. Now, just so we know, before moving on, for Python here, our overall runtime is not what I've listed here, but this is what the actual runtime of the merge sort algorithm looks like. So the merge step runs in linear time, and the split step takes logarithmic time for an overall n times log n. And that is how merge sort actually works. Okay, so what about space complexity? The merge sort algorithm takes linear space, and this is weird to think about at first, but as always, a visualization helps. So if we start at the top again with our full list and carry out the split method until we have single element lists, each of these new lists take up a certain amount of space. So at the second level here, we have two lists where each take up an n by 2 amount of space. Now this makes it seem that the sum of all this space is the additional space needed for merge sort, but that's not actually the case. In reality, there are two factors that make a difference. First, not every single one of these sublists are created simultaneously. At step 2, we create two n by 2 size sublists. When we move to the next step, however, we don't hold on to the n by 2 sublists and then create 4 n by 4 size sublists for the next split. Instead, after the 4 n by 4 size sublists are created, the n by 2 ones are deleted from memory. There's no reason to hold on to them any longer. Now the second point is that our code doesn't execute every path simultaneously. Think of it this way. When we pass our list to the top level merge sort function, our implementation calls split, which returns a left half and a right half. The next line of code then calls merge sort on the left half again. This runs the function, the merge sort function, again with a new list. In that second run of the function, split is called again. We get a second left and right half, and then again, like before, we call merge sort on this left half as well. What this means is that the code walks down the left path all the way down until that initial left half is sorted and merged back into one array. Then it's going to walk all the way down the right path and sort that until we're back to that first split with two n by 2 sized sublists. Essentially, we don't run all of these paths of code at once, so the algorithm doesn't need additional space for every sublist. In fact, it is the very last step that matters. In the last step, the two sublists are merged back into the new sorted list and returned. That sorted list has an equal number of items as the original unsorted list. And since this is a new list, it means that at most, the additional space the algorithm will require at a given time is n. Yes, at different points in the algorithm, we require log n amount of space, but log n is smaller than n, and so we consider the space complexity of merge sort to be linear because that is the overall factor. Okay, that was a lot, so let's stop here. Don't worry if you've got questions about merge sort because we're not done yet. Over the next few videos, let's wrap up this course by implementing merge sort on a linked list.
Over the last few videos, we implemented the merge sort algorithm on the array or list type in Python. Merge sort is probably the most complicated algorithm we've written so far, but in doing so, we learned about an important concept, divide and conquer. We also concluded the last video by figuring out the runtime of merge sort based on our implementation. Over the next few videos, we're going to implement merge sort again, this time on the linked list type. In doing so, we're going to get a chance to see how the implementation differs based on the data structure, while still keeping the fundamentals of the algorithm the same, and we'll also see how the runtime may be affected by the kinds of operations we need to implement.
Let's create a new file to put our second implementation of merge sort in. So file over here, new file, and this is going to have a rather long name. We'll call this linked list merge sort with underscores everywhere, .py. We're going to need the linked list class that we created earlier, so we'll start at the top by importing the linked list class from the linked list.py file. The way we do that is we'll say from linked list import linked list, right? So that imports the class. Let's test if this works really quick. We'll just do something like L equal linked list, L.add 10 or 1, doesn't matter, print L. Okay, and if I hit save, and then down here we'll say Python linked list merge sort.py. Okay, it works. So this is how we get some of the code, how we reuse the code that we've written in other files into this current file. We can get rid of this now. Okay, like we did with the first implementation of merge sort, we're going to split the code up across 3 functions. The main function merge sort, a split function, and a merge function. Now, if you were to look up a merge sort implementation in Python, both for a regular list, an array, or a linked list, you would find much more concise versions out there. But they're kind of hard to explain, so splitting it up into 3 will sort of help it, be easier to understand. So we'll call this merge sort at the top level, and this time it's going to take a linked list. Let's add a docstring to document the function. So we'll say that this function sorts a linked list in ascending order. And like before, we'll add the steps in here. So we'll say we first recursively divide the linked list into sublists containing a single node. Then we repeatedly merge these sublists to produce sorted sublists until one remains. And then finally, this function returns a sorted linked list. The implementation of this top-level merge function is nearly identical to the array or list version we wrote earlier. So first, we'll provide a stopping condition or 2. If the size of the list is 1, or it's an empty list, we'll return the linked list since it's naively sorted. So if linked list.size, remember that function we wrote, equal 1, then we'll return linked list. Else if linked list.head is none, meaning it's an empty list, then we'll return linked list as well. Okay, next let's split the linked list into a left and right half. Conceptually, this is no different, but in practice, we need to actually traverse the list. We'll implement a helper method to make this easier. But we'll say left half, comma, right half, equal split linked list. Now, once we have 2 sublists like before, we can call merge sort, the top level function, on each. So left equal merge sort, left half, and right equal merge sort on the right half. Finally, we'll merge these 2 top-level sublists and return it. So merge left and right. Okay, nothing new here, but in the next video, let's implement the split logic. The next step in the merge sort algorithm is the divide step, or rather, an implementation of the split function. So down here, we'll call this split like before, and this is going to take a linked list. Documenting things is good, and we've been doing it so far, so let's add a docstring. Divide the unsorted list at midpoint into sublists. Now, of course, when I say sublists here, I mean sublinked lists, but that's a long word to say. Now, here's where things start to deviate from the previous version. With the list type, we could rely on the fact that finding the midpoint using an index and list slicing to split into 2 lists would work even if an empty list was passed in. Since we have no automatic behavior like that, we need to account for this when using a linked list. So our first condition is if the linked list is none or if it's empty. That is, if head is equal to none. So we'll say if linked list equal none, or you can write is there, doesn't matter, or linked list.head is none. Well, linked list can be none, for example, if we call split on a linked list containing a single node. A split on such a list would mean left would contain the single node, while right would be none. Now, in either case, we're going to assign the entire list to the left half and assign none to the right. So we'll say left half equal linked list, and then right half equal none. You could also assign the single element list or none to left, and then create a new empty linked list to assign to the right half, but that's unnecessary work. So now that we've done this, we can return left half and right half. So that's our first condition. Let's add an else clause to account for non-empty linked lists. First, we'll calculate the size of the list. Now this is easy because we've done the work already, and we can just call the size method that we've defined. We'll say size equal linked_list.size. Using the size, we can determine the midpoint. So mid equals size, and here we'll use that floor division operator to divide it by 2. Once we have the midpoint, we need to get the node at that midpoint. Now, make sure you hit Command S to save here, and we're going to navigate back to linkedList.py. In here, we're going to add a convenience method at the very bottom, right before the repr function, right here. And this convenience method is going to return a node at a given index. So we'll call this node at index, and it's going to take an index value. This way, instead of having to traverse the list inside of our split function, we can simply call node at index and pass it the midpoint index we calculated to give us the node right there so we can perform the split. Okay, so this method accepts as an argument the index we want to get the node for. If this index is 0, then we'll return the head of the list. So if index == 0, return self.head. The rest of the implementation involves traversing the linked list and counting up to the index as we visit each node. The rest of the implementation involves traversing the linked list and counting up to the index as we visit each node. So I'll add an else clause here, and we'll start at the head. So we'll say current equal self.head. Let's also declare a variable called position to indicate where we are in the list. We can use a while loop to walk down the list. Our condition here is as long as the position is less than the index value. So I'll say while position is less than index. Inside the loop, we'll assign the next node to current and increment the value of position by 1. So current equal current.nextNode position plus equal 1. Once the position value equals the index value, current refers to the node we're looking for, and we can return it. We'll say return current. Let's get rid of all this empty space. There we go. Now back in linked list merge sort.py, we can use this method to get at the node after we've calculated the midpoint to get the node at the midpoint of the list. So we'll say mid node equal linked list dot node at index. And here I'm going to do something slightly confusing. I'm going to do mid minus 1. Remember, we're subtracting 1 here because we used size to calculate the midpoint. And like the len function, size will always return a value greater than the maximum index value. So think of a linked list with 2 nodes. Size would return 2. The midpoint, though, and the way we're calculating the index, we always start at 0, which means size is going to be 1 greater than that. So we're going to deduct 1 from it to get the value we want. But we're using the floor division operator, so it's going to round that down even more. No big deal. With the node at the midpoint, now that we have this mid node, we can actually split the list. So first, we're going to assign the entire linked list to a variable named left half. So left half equal linked list. This seems counterintuitive, but it'll make sense in a second. For the right half, we're going to assign a new instance of linked list. So right half equal linked list. This newly created list is empty, but we can fix that by assigning the node that comes after the midpoint. So after the midpoint of the original linked list, we can assign the node that comes after that midpoint node as the head of this newly created right linked list. So here we'll say right half dot head equal mid node dot next node. Once we do that, we can assign none to the next node property on mid node to effectively sever that connection and make what was the mid node now the tail node of the left linked list. So I'll say mid node dot next node equal none. If that's confusing, here's a quick visualization of what just happened. We start off with a single linked list and find the midpoint. The node that comes after the node at midpoint is assigned to the head of a newly created linked list, and the connection between the midpoint node and the one after is removed. We now have two distinct linked lists split at the midpoint. And with that, we can return the two sublists. So we'll return left half and right half. In the next video, let's tackle our merge function. In the last video, we defined an implementation for the version of the split function that works on linked lists. It contained a tiny bit more code than the array or list version, and that was expected. The merge function is no different because, like with the split function, after we carry out a comparison operation, we also need to swap references to corresponding nodes. All right, let's add our merge function over here at the bottom below the split function. So we'll call this merge, and it's going to take a left and a right. Now, because this can get complicated, we're going to document this function extensively. And as always, we're going to start with a docstring. So we'll say that this function merges two linked lists, sorting by data in the nodes. And it returns a new merged list. Remember that in the merge step, we're going to compare values across two linked lists and then return a new linked list with nodes where the data is sorted. So first, we need to create that new linked list. Let's add a comment in here. We'll say create a new linked list that contains nodes from, let's add it on a new line, merging left and right. Okay, and then create the list. So merged equal new linked list. To this list, we're going to do something unusual. We're going to add a fake head. This is so that when adding sorted nodes, we can reduce the amount of code we have to write by not worrying about whether we're at the head of the list. Once we're done, we can assign the first sorted node as the head and discard the fake head. Now, this might not make sense at first, but not having to worry about whether the new linked list already contains a head or not makes the code simpler. We'll add another comment, add a fake head that is discarded later. We'll say merged.add 0. Like we've been doing so far, we'll declare a variable named current to point to the head of the list. Set current to the head of the linked list, and then current equal merged.head. Next, we'll get a reference to the head on each of the linked lists, left and right. So we'll say obtain head nodes for left and right linked lists. And here we'll call this left head equal left.head and right head equal right.head. Okay, so with that setup out of the way, let's start iterating over both lists. So another comment, iterate over left and right as long, or we'll say until we reach the tail node of either. And we'll do that by saying while left head or right head. So this is a pattern that we've been following all along. We're going to iterate until we hit the tail nodes of both lists, and we'll move this pointer forward every time so that we traverse the list with every iteration. If you remember the logic behind this from the earlier version, once we hit the tail node of one list, if there are nodes left over in the other linked list, we don't need to carry out a comparison operation anymore, and we can simply add those nodes to the merged list. The first scenario we'll consider is if the head of the left linked list is none. This means we're already past the tail of left, and we can add all the nodes from the right linked list to the final merged list. So here I'll say if the head node of left is none, we're past the tail. Add the node from right to merged linked list. So here we'll say if left head is none, current.next node. Remember, current points to the head of the merge list that we're going to return. So here we're setting its next node reference to the head node on the right linked list. So here we'll say right head. Then when we do that, we'll move the right head forward to the next node. So we'll say right head equal right head dot next node. This terminates the loop on the next iteration. Let's look at a visualization to understand why. Let's say we start off with a linked list containing 4 nodes. So we keep calling split on it until we have lists with just a single head. Single node linked lists essentially. So let's focus on these 2 down here that we'll call left and right. We haven't implemented the logic for this part yet, but here we would compare the data values and see which one is less than the other. So we'll assume that left's head is lesser than right's head, so we'll set this as the next node in the final merged list. Left is now an empty linked list, so left.head equals none. On the next pass through the loop, left head is none, which is the situation we just implemented. Here, we can go ahead and now assign right head as the next node in the merge linked list. We know that right is also a singly linked list. Here's the crucial bit. When we move the pointer forward by calling next node on the right node, there is no node, and the right linked list is also empty now, which means that both left head and right head are none, and either one of these would cause our loop condition to terminate. So what we've done here is encoded a stopping condition for the loop. So we need to document this because it can get fuzzy. So right above that line of code, I'll say call next on right to set loop condition to false. Okay, there's another way we can arrive at this stopping condition, and that's in the opposite direction. If we start with the right head being none. So here we'll say, I'm going to add another comment. If, oops, not there, there. If the head node of right is none, we're past the tail. Then we'll say, add the tail node from left to merged linked list. And then we'll add that condition. We'll say else if right head is none. Now remember, we can enter these, even if left head is none, we can still go into this condition. We can still enter this if statement and execute this logic because the while loop, the loop condition here, is an or statement. So even if left head is false, if this returns true because there's a value there, there's a node there, the loop will keep going. Okay, now in this case, we want to set the head of the left linked list as the next node on the merge list. So this is simply the opposite of what we did over here. We'll set current.next node equal to left head. And then we'll move, so after doing that, we can move the variable pointing to left head forwards, which as we saw earlier is past the tail node and then results in the loop terminating. So we'll say left head equal left head dot next node. And we'll add that comment here as well. So we'll say call next on left to set loop condition to false. Because here, right head is none, and now we make left head none. These 2 conditions we looked at where either the left head or right head were at the tail nodes of our respective lists. Those are conditions that we run into when we've reached the bottom of our split, where we have single element linked lists or empty linked lists. Let's account for our final condition, where we're evaluating a node that is neither the head nor the tail of the list. And this condition, we need to reach into the nodes and actually compare the data values to one another before we can decide which node to add first to the merged list. So here, this is an else because we've arrived at our third condition, third and final. And here we'll say not at either tail node, obtain node data to perform comparison operations. So let's get each of those data values out of the respective nodes so that we can compare it. So we'll say left data equal left head dot data and right data equal right head dot data. Okay, what do we do next? Well, we compare. But first, let's add a comment. So we'll say if data on left is less than right, set current to left node. And then move, actually we'll add this in a second. So here we'll say if left data is less than right data, then current dot next node equal left head. And then we'll add a comment and we'll say move left head to next node on that list. So we'll say left head equal left head dot next node. Just as our comment says, we'll check if the left data is less than the right data. If it is, since we want a list in ascending order, we'll assign the left node to be the next node in the merged list. We'll also move the left head forward to traverse down to the next node in that particular list. Now, if left is larger than right, then we want to do the opposite. So we'll go back to spaces, we'll add another comment. If data on left is greater than right, set current to right node. Okay, so else. Here we assign the right head to be the next node in the merged list. So current.nextNode equal right head. And then comment, move right head to next node. So right head equal right head dot next node. Okay, after doing that, we move the right head pointer to reference the next node in the right list. And finally, at the end of each iteration of the while loop, so not here, but 2 spaces back, right? Make sure we're indented at the same level as the while. So we got to go, yep, or not the same level as the while, but the same outer scope. And then there, we're going to say, move current to next node. So current equal current dot next node. Okay, don't worry if this is confusing. As always, we'll look at a visualization in just a bit. So we'll wrap up this function by discarding that fake head we set earlier, setting the correct node as head, and returning the linked list. So we'll add a comment, discard fake head, and set first merged node as head. So here we'll say head equal merged dot head dot next node, and then merged dot head equal head, and finally return merged. Okay, we wrote a lot of code here. A lot of it was comments, but still it's a bunch. Let's take a quick break. In the next video, we'll test this out, evaluate our results, and determine the runtime of our algorithm. Okay, first things first, let's test out our code. Now we'll keep it simple because writing a robust verify function would actually take up this entire video. Instead, I'll leave that up to you to try as homework. Okay, so at the very end, let's create a new linked list. Let's add a few nodes to this. So ladd, I'm going to copy paste this so it makes it easier for me to not to have to retype a bunch. So I'll add 10, then say 2, 44, 15, and something like 200. Okay, then we'll go ahead and print L so that we can inspect this list. Next, let's declare a variable here. So we'll call this sorted linked list. And to this, we're going to assign the result of calling merge sort on L, and then we'll print this. So sorted linked list. Okay, since we've taken care of all the logic, we know that this gets added in as nodes. And then let's see what this looks like. All right, so hit save, and then bring up the console. We're going to type out Python linked list underscore merge sort dot py, and then enter. Okay, so we see that linked list we first created. Remember that what we add first, right, that eventually becomes the tail. So 10 is the tail, 200 is the last one, so 200 is the head. Because I'm calling add, it simply adds each one to the head of the list. So here we have 10, 2, 44, 15, and 200 in the order we added. And then the sorted linked list sorts it out. So it's 2, 10, 15, 44, and 200. Look at that, a sorted linked list. Okay, so let's visualize this from the top. We have a linked list containing 5 nodes with integers 10, 2, 44, 15, and 200 as data respectively. Our merge sort function calls split on this list. The split function calls size on the list and gets back 5, which makes our midpoint 2. Using this midpoint, we can split the list using the node at index method. Remember that when doing this, we deduct 1 from the value of mid, So we're going to split here using an index value of 1. Effectively, this is the same. Since we're starting with an index value of 0, 1 means we split after node 2. We assign the entire list to left half, then create a new list and assign that to right half. We can assign node 3 at index value 2 as the head of the right list and remove the references between node 2 and node 3. So far so good, right? Okay, so now we're back in the merge sort function after having called split, and we have 2 linked lists. Let's focus on just the left half, because if you go back and look at our code, we're going to call merge sort on the left linked list again. This means the next thing we'll do is run through that split process. Since this is a linked list containing 2 nodes, this means that split is going to return a new left and right list, each with 1 node. Again, we're back in the merge sort function, which means that we call merge sort on this left list again. Since this is a single node linked list, on calling merge sort on it, we immediately return before we split since we hit that stopping condition. So we go to the next line of code, which is calling merge sort on the right list as well. But again, we'll get back immediately because we hit that stopping condition. Now that we have a left and right that we get back from calling merge sort, we can call merge on them. Inside the merge function, we start by creating a new linked list and attaching a fake head. Then we evaluate whether either the left or the right head is none. Since neither condition is true, we go to the final step where we evaluate the data in each node. In this case, the data in the right node is less than the left node, so we assign the right node as the next node in the merge linked list and move the right head pointer forward. In the merge linked list, we move our current pointer forward to this new node we've added, and that completes one iteration of the loop. On the next iteration, right head now points to none, since that was a single node list, and we can assign the rest of the left linked list, which is effectively the single node, over to the merge linked list. Here, we discard the fake head, move the next node up to be the correct head, and return the newly merged sorted linked list. Remember that at this point, because right head and left head pointed to none, our while loop terminated. So in this way, we recursively split and repeatedly merge sublists until we're back with one sorted linked list. The merge sort algorithm is a powerful sorting algorithm, but ultimately it doesn't really do anything complicated. It just breaks the problem down until it's really simple to solve. Remember the technique here, which we've talked about before, is called divide and conquer. So I like to think of merge sort in this way. There's a teacher at the front of the room, and she has a bunch of books that she needs to sort into alphabetical order. Instead of doing all that work herself, she splits that pile into 2 and hands it to 2 students at the front. Each of those students split it into 2 more and hand it to the 4 students seated behind them. As each student does this, eventually, a bunch of single students has 2 books to compare, and they can sort it very easily and hand it back to the student who gave it to them in front of them, who repeats the process backwards. So ultimately, it's really simple work, it's just efficiently delegated. Now back to our implementation here, let's talk about runtime. So far, other than the node swapping we had to do, it seems like most of our implementation is the same, right? In fact, it is, including the problems that we ran into in the list version as well. So in the first implementation of merge sort, we thought we had an algorithm that ran in big O of n log n, but turns out we didn't. Why? Well, the Python list slicing operation, if you remember, actually takes up some amount of time amounting to big O of k. A true implementation of merge sort runs in quasi-linear or log-linear time, that is, n times log n. So we almost got there, but we didn't. Now, in our implementation of merge sort on a linked list, we introduce the same problem. So if we go back up to the merge, or rather the split function, this is where it happens. Now, swapping node references, that's a constant time operation. No big deal. Comparing values, also constant time. The bottleneck here, like list slicing, is in splitting a linked list at the midpoint. If we go back to our implementation, you can see here that we use the node at index method, which finds the node we want by traversing the list. This means that every split operation incurs a big O of k cost, where k here is the midpoint of the list, effectively n by 2, because we have to walk down the list, counting up the index until we get to that node. Given that overall splits take logarithmic time, our split function, just like the one we wrote earlier, incurs a cost of big O of k log n. So here we'll say it takes big O of k times log n. Now the merge function, also like the one we wrote earlier, takes linear time. So that one is good. That one runs in the expected amount of time. So here we'll say it runs in linear time. And that would bring our overall runtime, so up at the merge sort function, we can say this runs in big O of kn times log n. It's okay though, this is a good start. And one day when we talk about constant factors and look at ways we can reduce the cost of these operations using different strategies, we can come back and reevaluate our code to improve our implementation. For now, as long as you understand how merge sort works conceptually, what the runtime and space complexities look like, and where the bottlenecks are in your code, that's plenty of stuff. If you're interested in learning more about how we would solve this problem, check out the notes in the teacher's video. In the next video, let's wrap this course up.
And with that, let's wrap up this course. In the prerequisite to this course, Introduction to Algorithms, we learned about basic algorithms along with some concepts like recursion and big O that set the foundation for learning about implementing and evaluating algorithms. In this course, we learned what a data structure is and how data structures go hand in hand with algorithms. We started off by exploring a data structure that many of us use in our day-to-day programming, arrays, or lists as they're known in Python. We took a peek under the hood at how arrays are created and stored, and examined some of the common operations carried out on arrays. These are operations that we write and execute all the time, but here we took a step back and evaluated the run times of these operations and how they affect the performance of our code. After that, we jumped into an entirely new world where we wrote our own data structure, a singly linked list. Admittedly, linked lists aren't used much in day-to-day problem solving, but it is a good data structure to start off with because it is fairly straightforward to understand and not that much different from an array. We carried out the same exercise as we did on arrays in that we looked at common data operations, but since this was a type we defined on our own, we implemented these operations ourselves and got to examine with a fine-tooth comb how our code and the structure of the type affected the runtime of these operations. The next topic we tackled was essentially worlds colliding. We implemented a sorting algorithm to sort two different data structures. Here we got to see how all of the concepts we've learned so far, algorithmic thinking, time and space complexity, and data structures all come together to tackle the problem of sorting data. This kind of exercise is one we're going to focus on moving forward as we try to solve more real-world programming problems using different data structures and algorithms. If you've stuck with this content so far, keep up the great work. This can be a complex topic, but a really interesting one, and if you take your time with it, you will get a deeper understanding of programming and problem solving. As always, check the notes for more resources and happy coding.
You may have heard that algorithms in computer science are boring or frustrating. They certainly can be hard to figure out, especially the way some textbooks explain them. But once you understand what's going on, algorithms can seem fascinating, clever, or even magical. To help further your understanding of algorithms, this course is going to look at two categories: sorting algorithms and searching algorithms. You could argue that these are the easiest kinds of algorithms to learn. But in learning how these algorithms are designed, we'll cover useful concepts like recursion and divide and conquer that are used in many other sorts of algorithms, and can even be used to create brand new ones. By the way, all the code samples I'm going to show in the videos will be in Python because it's a popular language that's relatively easy to read, but you don't need to know Python to benefit from this course. You can see the teacher's notes for each video for info on implementing these algorithms in your own favorite language. Our goal with this course is to give you an overview of how sorting and searching algorithms work. But many algorithms have details that can be handled in different ways. Some of these details may distract from the big picture, so we've put them in the teacher's notes instead. You don't need to worry about these when completing the course for the first time, but if you're going back and referring to it later, be sure to check the teacher's notes for additional info. Suppose we have a list of names. It's a pretty big list, 100,000 names long. This list could be part of an address book or social media app. And we need to find the locations of individual names within the list, possibly to look up additional data that's connected to the name. Let's assume there's no existing function in our programming language to do this, or that the existing function doesn't suit our purpose in some way. For an unsorted list, our only option may be to use linear search, also known as sequential search. Linear search is covered in more detail elsewhere on our site. Check the teacher's notes for a link if you want more details. You start at the first element. You compare it to the value you're searching for. If it's a match, you return it. If not, you go to the next element. You compare that to your target. If it's a match, you return it. If not, you go to the next element, and so on through the whole list. The problem with this is that you have to search the entire list every single time. We're not doing anything to narrow down the search each time. We have to search all of it. If you're searching a big list or searching it repeatedly, this amount of time can slow your whole app down to the point that people may not want to use it anymore. That's why it's much more common to use a different algorithm for searching lists, binary search. Binary search is also covered in more detail elsewhere on our site. Check the teacher's notes for a link. Binary search does narrow the search down for us. Specifically, it lets us get rid of half the remaining items we need to search through each time. It does this by requiring that the list of values be sorted. It looks at the value in the middle of the list. If the value it finds is greater than the target value, it ignores all values after the value it's looking at. If the value it finds is less than the target value, it ignores all values before the value it's looking at. Then it takes the set of values that remain and looks at the value in the middle of that list. Again, if the value it finds is greater than the target value, it ignores all values after the value it's looking at. If the value it finds is less than the target value, it ignores all values before the value it's looking at. But, as we mentioned, binary search requires the list of values you're searching through to be sorted. If the list weren't sorted, you would have no idea which half of the values to ignore, because either half could contain the value you're looking for. You'd have no choice but to use linear search. So before we can use binary search on a list, we need to be able to sort that list. We'll look at how to do that next. Our end goal is to sort a list of names, but comparing numbers is a little easier than comparing strings, so we're going to start by sorting a list of numbers. I'll show you how to modify our examples to sort strings at the end of the course. To help make clear the importance of choosing a good sorting algorithm, we're going to start with a bad one. It's called BOGO sort. Basically, BOGO sort just randomizes the order of the list repeatedly until it's sorted. Here's a Python code file where we're going to implement BOGO sort. It's not important to understand this code here at the top, although we'll have info on it in the teacher's notes if you really want it. All you need to know is that it takes the name of a file that we pass on the command line, loads it, and returns a Python list, which is just like an array in other languages, containing all the numbers that it read from the file. Let me have the program print out the list of numbers it loads so you can see it. We'll call the print method, and we'll pass it the list of numbers. Save that. Let's run it real quick with python bogosort.py. Oh, whoops. And we need to provide it the name of the file here on the command line that we're going to load. So it's in the numbers directory. A slash separates the directory name from the file name. 5.txt. And there's our list of numbers that was loaded from the file. Okay, let me delete that print statement and then we'll move on. BOGO sort just randomly rearranges the list of values over and over. So the first thing we're going to need is a function to detect when the list is sorted. We'll write an isSorted function that takes a list of values as a parameter. It'll return true if the list passed in is sorted, or false if it isn't. We'll loop through the numeric index of each value in the list, from 0 to 1 less than the length of the list. Like many languages, Python list indexes begin at 0, so a list with a length of 5 has indexes going from 0 through 4. If the list is sorted, then every value in it will be less than the one that comes after it. So we test to see whether the current item is greater than the one that follows it. If it is, it means the whole list is not sorted, so we can return false. If we get down here, it means the loop completed without finding any unsorted values. Python uses whitespace to mark code blocks, so unindenting the code like this marks the end of the loop. Since all the values are sorted, we can return true. Now we need to write the function that will actually do the so-called sorting. The BOGOsort function will also take the list of values it's working with as a parameter. We'll call our isSorted function to test whether the list is sorted. We'll keep looping until isSorted returns true. Python has a ready-made function that randomizes the order of elements in a list. Since the list isn't sorted, we'll call that function here. And since this is inside the loop, it'll be randomized over and over until our isSorted function returns true. If the loop exits, it means isSorted returned true and the list is sorted, so we can now return the sorted list. Finally, we need to call our BOGOsort function, pass it the list we loaded from the file, and print the sorted list it returns. Okay, let's save this and try running it. We do so with Python, the name of the script, bogosort.py, and the name of the file we're going to run it on, numbers directory 5.txt. It looks like it's sorting our list successfully. But how efficient is this? Let's add some code to track the number of times it attempts to sort the list. Up here at the top of the BOGOsort function, we'll add a variable to track the number of attempts it's made. We'll name it attempts, and we'll set its initial value to 0, since we haven't made any attempts yet. With each pass through the loop, we'll print the current number of attempts. And then here at the end of the loop, after attempting to shuffle the values, we'll add one to the count of attempts. Let's save this, and let's try running it again a couple times. In the console, I can just press the up arrow to bring up the previous command and rerun it. So it looks like this first run to sort this 5-element list took 363 attempts. Let's try it again. This time it only took 91 attempts. We're simply randomizing the list with each attempt, so each run of the program takes a random number of attempts. Now let's try this same program with a larger number of items. Python BOGOsort numbers. I have a list of 8 items set up here in this other file. This time it takes 11,000 attempts. Only 487 this time. And this time 13,000. You can see that the trend is increasing steadily. The problem with BOGOsort is that it doesn't make any progress toward a solution with each pass. It could generate a list where just one value is out of order, but then on the next attempt it could generate a list where all the elements are out of order again. Stumbling on a solution is literally a matter of luck, and for lists with more than a few items, it might never happen. Up next, we'll look at selection sort. It's a sorting algorithm that's still slow, but it's better than BOGOsort. Previously, we showed you BOGOsort, a terrible sorting algorithm that basically randomizes the order of a list and then checks to see if it happens to be sorted. The problem with BOGOsort is that it doesn't get any closer to a solution with each operation, and so with lists that have more than a few items, it'll probably never finish sorting them. Now we're going to look at an algorithm named selection sort. It's still slow, but at least each pass through the list brings it a little closer to completion. Our implementation of selection sort is going to use 2 arrays, an unsorted array and a sorted one. Some versions move values around within just one array, but we're using 2 arrays to keep the code simpler. The sorted list starts out empty, but we'll be moving values from the unsorted list to the sorted list one at a time. With each pass, we'll look through each of the values in the unsorted array, find the smallest one, and move that to the end of the sorted array. We'll start with the first value in the unsorted array, and say that's the minimum, or smallest value we've seen so far. Then we'll look at the next value and see if that's smaller than the current minimum. If it is, we'll mark that as the new minimum. Then we'll move to the next value and compare that to the minimum again. If it's smaller, that becomes the new minimum. We continue that way until we reach the end of the list. At that point, we know whatever value we have marked as the minimum is the smallest value in the whole list. Now, here's the part that makes selection sort better than BOGOsort. We then move that minimum value from the unsorted list to the end of the sorted list. The minimum value isn't part of the unsorted list anymore, so we don't have to waste time looking at it anymore. All our remaining comparisons will be on the remaining values in the unsorted list. Then we start the process over. At this point, our list consists of the numbers 8, 5, 4, and 7. Our first minimum is 8. We start by comparing the minimum to 5. 5 is smaller than 8, so 5 becomes the new minimum. Then we compare 5 to 4, and 4 becomes the new minimum. 4 is not smaller than 7, though, so 4 remains the minimum. 4 gets moved to the end of the sorted array, becoming its second element. The process repeats again. 8 is the first minimum, but 5 is smaller, so that becomes the minimum. 7 is larger, so 5 stays as the minimum. And 5 is what gets moved over to the sorted array. And so on, until there are no more items left in the unsorted array, and all we have left is the sorted array. So that's how selection sort works in general. Now let's do an actual implementation of it. This code here at the top is the same as we saw in the BOGO sort example. It just loads a Python list of numbers from a file. Let's implement the function that will do our selection sort. We're going to pass in our Python list containing all the unsorted numbers. We'll create an empty list that will hold all our sorted values. We'll loop once for each value in the list. We call a function named indexOfMin, which we're going to write in just a minute, that finds the minimum value in the unsorted list and returns its index. Then we call the pop method on the list and pass it the index of the minimum value. Pop will remove that item from the list and return it. We then add that value to the end of the sorted list. Going up a level of indentation signals to Python that we're ending the loop. After the loop finishes, we return the sorted list. Now we need to write the function that picks out the minimum value. We pass in the list we're going to search. We mark the first value in the list as the minimum. It may or may not be the actual minimum, but it's the smallest we've seen on this pass through the list. It's also the only value we've seen on this pass through the list so far. Now we loop through the remaining values in the list after the first. We test whether the value we're currently looking at is less than the previously recorded minimum. If it is, then we set the current index as the new index of the minimum value. After we've looped through all the values, we return the index of the smallest value we found. Lastly, we need to actually run our selection sort method and print the sorted list it returns. Let's save this, and now let's try running it. We run the Python command and pass it the name of our script, selectionsort.py. In the numbers directory, I've saved several data files filled with random numbers, one on each line. 5.txt has 5 lines, 8.txt has 8 lines, and to help us really measure the speed of our algorithms, 10,000.txt has 10,000 lines. I've even created a file with 1,000,000 numbers. Our script takes the path of a file to load as an argument, so I'll give it the path of our file with 5 numbers, numbers/5.txt. The script runs, reads the numbers in the file into a list, calls our selection sort method with that list, and then prints the sorted list. Let me add a couple print statements within the selection sort function so you can watch the sort happening. Don't worry about figuring out the Python formatting string that I use, it's just there to keep the two lists neatly aligned. I'll add the first print statement before the loop runs at all. I'll have it print out the unsorted list and the sorted list. I'll add an identical print statement within the loop so we can watch values moving from the unsorted list to the sorted list. Let's save this. And we'll try running the same command again. The output looks like this. You can see the unsorted list on the left and the sorted list on the right. Initially, the sorted list is empty. On the first pass, it selects the lowest number, 1, and moves it to the sorted list. Then it moves the next lowest number over, 4. This repeats until all the numbers have been moved to the sorted list. I have another file with 8 different numbers in it. Let's try our program with that. Python selection sort.py numbers 8.txt. You can see the same process at work here. Notice that this file had some duplicate values too. That's okay though, because the indexOfMin function only updates the minimum index if the current value is less than the previous minimum. If they're equal, it just keeps the first minimum value it found, and waits to move the duplicate value over until the next pass through the list. So now we know that the selection sort algorithm works, but the data sets we've been giving it to sort are tiny. In the real world, algorithms need to work with data sets of tens of thousands or even millions of items and do it fast. I have another file with 10,000 random numbers in it. Let's see if selection sort can handle that. If I run this as it is now, though, it'll print out a lot of debug info as it sorts the list. So first I'm going to go into the program and remove the two print statements in the selection sort function. Now let's run the program again on the 10,000.txt file and see how long it takes. Python, selection sort.py, numbers, 10,000.txt. 1 1000, 2 1000, 3 1000, 4 1000, 5 1000, 6 1000, 7 1000, 8 1000, 9 1000, 10 1000, 11 1000, 12,000, 13,000, and it prints out all 10,000 of those numbers neatly sorted. It took a little bit though. How long? Well, counting the time off vocally isn't very precise, and other programs running on the system can skew the amount of time your program takes to complete. Let me show you a Unix command that's available here in Workspaces, which can help. You type time, followed by a space, and then the command you want to run. So this command by itself will print the contents of our 5.txt file, cat, as in concatenate, numbers, 5.txt. And this command will do the same thing, but it'll also keep track of how long it takes the cat program to complete and report the result. Time, cat, numbers, 5.txt. The real row in the results is the actual amount of time for when the program started running to when it completed. We can see it finished in a fraction of a second. But as we said, other programs running on the system can take CPU resources, in which case your program will seem slower than it is. So we generally want to ignore the real result. The user result is the amount of time that the CPU actually spent running the program code. So this is the total amount of time the code inside the cat program took to run. The sys result is the amount of time the CPU spent running Linux kernel calls that your code made. The Linux kernel is responsible for things like network communications and reading files, so loading the 5.txt file is probably included in this result. In evaluating code's performance, we're generally going to want to add together the user and sys results. But cat is a very simple program. Let's try running the time command on our code and see if we get a more interesting result. Time, Python, selection sort.py, numbers, 10,000.txt. This takes much longer to complete, nearly 12 seconds according to the real-time measurement. But as we said, the real result is often skewed, so let's disregard that. If we add the user and sys runtimes together, we get about 6 seconds. The time for the program to complete will vary a little bit each time you run it, but if it's doing the same operations, it usually won't change more than a fraction of a second. If I run our selection sort script on the same file, you can see it completes in roughly the same time. Now let's try it on another file with 1 million numbers. Time, Python, selection sort.py, numbers, 1 million.txt. How long does this one take? I don't even know. While designing this course, I tried running this command, and my workspace connection timed out before it completed. So we'll just say that selection sort takes a very, very long time to sort 1 million numbers. If we're going to sort a list that big, we're going to need a faster algorithm. We'll look into alternative sorting algorithms shortly. The next two sorting algorithms we look at will rely on recursion, which is the ability of a function to call itself. So before we move on, we need to show you how recursion works. Recursive functions can be very tricky to understand. Imagine a row of dominoes stood on end, where one domino falling over causes the next domino to fall over, which causes the next domino to fall over, causing a chain reaction. It's kind of like that. Let's suppose we need to write a function that adds together all the numbers in an array, or in the case of Python, a list. Normally, we'd probably use a loop for this sort of operation. The function takes a list of the numbers we want to add. The total starts at 0. We loop over every number contained in the list, and we add the current number to the total. Once we're done looping, we return the accumulated total. If we call this sum function with a list of numbers, it'll return the total. When we run this program, it'll print out that return value, 19. Let's try it real quick. Python recursion.py. Oh, whoops. Mustn't forget to save my work here. And run it, and we see the result, 19. To demonstrate how recursion works, let's revise the sum function to use recursion instead. Note that recursion is not the most efficient way to add a list of numbers together. But this is a good problem to use to demonstrate recursion because it's so simple. One thing before I show you the recursive version, though. This example is going to use the Python slice syntax, so I need to take a moment to explain that for those not familiar with it. A slice is a way to get a series of values from a list. Let's load up the Python REPL or read evaluate print loop so I can demonstrate. We'll start by creating a list of numbers to work with. Numbers equals a list with 0, 1, 2, 3, and 4, containing those numbers. Like arrays in most other languages, Python list indexes start at 0, so numbers 1 will actually get the second item from the list. With slice notation, I can actually get several items back. It looks just like accessing an individual index of a list. But then I type a colon, followed by the list index that I want up to, but not including. So numbers 1, 4 would get us the second up to, but not including, the fifth items from the list. That is, it'll get us the second through the fourth items. Now I know what you're thinking, and you're right. That up to but not including rule is a little counterintuitive. But you can just forget all about it for now, because we won't be using a second index with any of our Python slice operations in this course. Here's what we will be using. When you leave the second index off of a Python slice, it gives you the items from the first index up through the end of the list, wherever that is. So numbers 1, with no index following it, will give us items from the second index up through the end of the list. Numbers 2, will give us items from the third index up through the end of the list. You can also leave the first index off to get everything from the beginning of the list. Numbers 3 will get us everything from the beginning of the list up to, but not including, the third index. It's also worth noting that if you take a list with only one item, and you try to get everything from the non-existent second item onwards, the result will be an empty list. So if I create a list with just one item in it, and I try to access from the second element onwards, the second element doesn't exist, so the result will be an empty list. Don't worry too much about remembering Python slice syntax. It's not an essential part of sorting algorithms or recursion. I'm only explaining it to help you read the code you're about to see. So I'm going to exit the Python REPL. Now that we've covered recursion, we can convert our sum function to a recursive function. It'll take the list of numbers to add, just like before. Now, here's the recursive part. We'll have the sum function call itself. We use slice notation to pass the entire list of numbers except the first one. Then we add the first number in the list to the result of the recursive function call and return the result. So if we call sum with 4 numbers first, it'll call itself with the remaining 3 numbers. That call to sum will then call itself with the remaining 2 numbers, and so on. But if we save this and try to run it, Python recursion.py, well, first we get a syntax error. It looks like I accidentally indented something I shouldn't have. So let me go fix that real quick. There we go. That suggested to Python that there was a loop or something there when there wasn't. So let's go back to the terminal and try running this again. There we go. Now we're getting the error I was expecting. Recursion error, maximum recursion depth exceeded. This happens because sum gets into an infinite loop. It keeps calling itself over and over. The reason is that when we get down to a list of just one element, and we take a slice from the non-existent second element to the end, the result is an empty list. That empty list gets passed to the recursive call to sum, which passes an empty list in its recursive call to sum, and so on until the Python interpreter detects too many recursive calls and shuts the program down. What we need is to add a base case to this recursive function, a condition where the recursion stops. This will keep it from getting into an infinite loop. With the sum function, the base case is when there are no elements left in the list. In that case, there is nothing left to add, and the recursion can stop. A base case is the alternative to a recursive case, a condition where recursion should occur. For the sum function, the recursive case is when there are still elements in the list to add together. Let's add a base case at the top of the function. Python treats a list that contains one or more values as a true value, and it treats a list containing no values as a false value. So we'll add an if statement that says if there are no numbers in the list, we should return a sum of 0. That way, the function will exit immediately, without making any further recursive calls to itself. We'll leave the code for the recursive case unchanged. If there are still numbers in the list, the function will call itself with any numbers after the first, then add the return value to the first number in the list. Let's save this, and try running it again. Python recursion.py. It'll output the sum of the numbers in the list, 19. But it's still not really clear how this worked. Let's add a couple print statements that will show us what it's doing. We'll show the recursive call to sum and what it's being called with. We'll also add a call to print right before we return, showing which of the calls to sum is returning and what it's returning. Let me save this and resize the console a bit. And let's try running it again. Python recursion.py. Since the print calls are inside the sum function, the first call to sum1279 isn't shown, only the recursive calls are. This first call to sum ignores the first item in the list, 1, and calls itself recursively. It passes the remaining items from the list, 2, 7, and 9. That call to sum again ignores the first item in the list it receives, 2, and again calls itself recursively. It passes the remaining items in the list, 7 and 9. That call ignores the 7 and calls itself with a 9. And the last call shown here ignores the 9 and calls itself with an empty list. At this point, none of our recursive calls to sum have returned yet. Each of them is waiting on the recursive call it made to sum to complete. Python and other programming languages use something called a call stack to keep track of this series of function calls. Each function call is added to the stack, along with the place in the code that it needs to return when it completes. But now the empty list triggers the base case, causing the recursion to end and the sum function to return 0. That 0 value is returned to its caller. The caller adds the 0 to the first and only value in its list, 9. The result is 9. That 9 value gets returned to the caller, which adds it to the first value in the list it received, 7. The result is 16. That 16 value is returned to the caller, which adds it to the first value in the list it received, 2. The result is 18. That 18 value is returned to the caller, which adds it to the first value in the list it received, 1. The result is 19. That 19 value is returned to the caller, which is not the sum function recursively calling itself, but our main program. This is our final result, which gets printed. It's the same result we got from the loop-based version of our program. The end. We don't want the print statements in our final version of the program, so let me just delete those real quick. And there you have it, a very simple recursive function. Well, the function is simple, but as you can see, the flow of control is very complex. Don't worry if you didn't understand every detail here, because we won't be using this particular example again. There are two fundamental mechanisms you need to remember. A recursive function needs a recursive case that causes it to call itself, and it also needs to eventually reach a base case that causes the recursion to stop. You've seen BOGO sort, which doesn't make any progress towards sorting a list with each pass. Either it's entirely sorted, or it isn't. You've seen selection sort, which moves one value over to a sorted list with each pass, so that it has fewer items to compare each time. Now let's look at an algorithm that speeds up the process further by further reducing the number of comparisons it makes. It's called quicksort. Here's some Python code where we'll implement quicksort. Again, you can ignore these lines at the top. We're just using them to load a file full of numbers into a list. The quicksort algorithm relies on recursion. To implement it, we'll write a recursive function. We'll accept the list of numbers to sort as a parameter. Quicksort is recursive because it keeps calling itself with smaller and smaller subsets of the list you're trying to sort. We're going to need a base case where the recursion stops, so it doesn't enter an infinite loop. Lists that are empty don't need to be sorted, and lists with just one element don't need to be sorted either. In both cases, there's nothing to flip around. So we'll make that our base case. If there are 0 or 1 elements in the list passed to the quicksort function, we'll return the unaltered list to the caller. Lastly, we need to call our quicksort function with our list of numbers and print the list it returns. That takes care of our base case. Now we need a recursive case. We're going to rely on a technique that's common in algorithm design called divide and conquer. Basically, we're going to take our problem and split it into smaller and smaller problems until they're easy to solve. In this case, that means taking our list and splitting it into smaller lists. Viewers, a suggestion. The process I'm about to describe is complex. There's just no way around it. If you're having trouble following along, remember the video playback controls. Feel free to slow the playback down, rewind, or pause the video as needed. After you watch this the first time, you may also find it helpful to rewind and make your own diagram of the process as we go. Okay, ready? Here goes. Suppose we load the numbers from our 8.txt file into a list. How do we divide it? It would probably be smart to have our quicksort function divide the list in a way that brings it closer to being sorted. Let's pick an item from the list. We'll just pick the first item for now, 4. We'll call this value we've picked the pivot, like the center of a seesaw on a playground. We'll break the list into 2 sublists. The first sublist will contain all the items in the original list that are smaller than the pivot. The second sublist will contain all the items in the original list that are greater than the pivot. The sublists of values less than and greater than the pivot aren't sorted. But what if they were? You could just join the sublists and the pivot all together into one list, and the whole thing would be sorted. So how do we sort the sublist? We call our quicksort function recursively on them. This may seem like magic, but it's not. It's the divide and conquer algorithm design technique at work. If our quicksort function works on the big list, then it will work on the smaller lists too. For our first sublist, we take the first item as the pivot again. That's 3. We break the sublist into 2 sublists, one with everything less than the pivot, and one with everything greater than the pivot. Notice that there's a value equal to the pivot that gets put into the less than sublist. Our finished quicksort function is actually going to put everything that's less than or equal to the pivot in the first sublist. But I don't want to say less than or equal to over and over, so I'm just referring to it as the less than pivot sublist. Also notice that there are no values greater than the pivot. That's okay. When we join the sublists back together, that just means nothing will be in the returned list after the pivot. We still have one sublist that's more than one element long, so we call our quicksort function on that too. You and I can see that it's already sorted, but the computer doesn't know that, so it'll call it anyway, just in case. It picks the first element, 2, as a pivot. There are no elements less than the pivot, and only one element greater than the pivot. That's it for the recursive case. We've finally hit the base case for our quicksort function. It'll be called on both the empty list of elements less than the pivot and the one-item list of elements greater than the pivot. But both of these lists will be returned as they are, because there's nothing to sort. So now at the level of the call stack above this, the returned sorted lists are used in place of the unsorted sublist that's less than the pivot and the unsorted sublist that's greater than the pivot. These are joined together into one sorted list. Remember that any empty lists get discarded. Then, at the level of the call stack above that, the returned sorted lists are used in place of the unsorted sublists there. Again, they were already sorted, but the quicksort method was called on them anyway just in case. The sublists are joined together into one sorted list. At the level of the call stack above that, the returned sorted list is used in place of the unsorted sublist that's less than the pivot. So now everything that's less than or equal to the pivot is sorted. Now we call quicksort on the unsorted sublist that's greater than the pivot, and the process repeats for that sublist. We pick the first element, 6, as the pivot. We split the sublist into sublists of elements that are less than and greater than this pivot. And we recursively call the quicksort function until those sublists are sorted. Eventually, a sorted sublist is returned to our first quicksort function call. We combine the sublist that's less than or equal to the pivot itself, and the sublist that's greater than the pivot into a single list. And because we recursively sorted the sublists, the whole list is sorted. So that's how the quicksort function is going to work. In the next video, we'll show you the actual code. Quicksort works by picking a pivot value, then splitting the full list into two sublists. The first sublist has all the values less than or equal to the pivot, and the second sublist has all the values greater than the pivot. The quicksort function recursively calls itself to sort these sublists, and then to sort the sublists of those sublists until the full list is sorted. Now it's time to actually implement this in code. We already have the base case written. Any list passed in that consists of 0 or 1 values will be returned as is because there's nothing to sort. Now we need to create a list that will hold all the values less than the pivot. That list will be empty at first. We do the same for values greater than the pivot. Next, we need to choose the pivot value. For now, we just grab the first item from the list. Then we loop through all the items in the list following the pivot. We check to see whether the current value is less than or equal to the pivot. If it is, we copy it to the sublist of values less than the pivot. Otherwise, the current value must be greater than the pivot, so we copy it to the other list. This last line is where the recursive magic happens. We call quicksort recursively on the sublist that's less than the pivot. We do the same for the sublist that's greater than the pivot. Those two calls will return sorted lists, so we combine the sorted values less than the pivot itself, and the sorted values greater than the pivot. That gives us a complete sorted list, which we return. This took a lot of prep work. Are you ready? Let's try running it. Python quicksort.py numbers 8.txt. It outputs our sorted list. I don't know about you, but this whole thing still seems a little too magical to me. Let's add a couple print statements to the program so we can see what it's doing. First, we'll add a print statement right before the first call to the quicksort function, so we can see the unsorted list. We'll also add a print right within the quicksort function, right before the recursive calls. Again, this string formatting code is just to keep the info aligned in columns. Let's try running this again. And now you can see our new debug output. Each time quicksort goes to call itself recursively, it prints out the pivot, as well as the sublist of items less than or equal to the pivot, if any, and the sublist of items greater than the pivot, if any. You can see that first it sorts the sublist of items less than the pivot at the top level. It goes through a couple levels of recursion to do that. There are actually additional levels of recursion, but they're from calls to quicksort with a list of 0 or 1 elements, and those calls return before the print statement is reached. Then it starts sorting the second sublist from the top level with items greater than the original pivot. You can see a couple levels of recursion for that sort as well. Finally, when both sublists are recursively sorted, the original call to the quicksort function returns, and we get the sorted list back. So we know that it works. The next question is, how well does it work? Let's go back to our file of 10,000 numbers and see if it can sort those. First, though, I'm going to remove our two debug calls to print so it doesn't produce unreadable output. A quick note, if you try running this on a file with a lot of repeated values, it's possible you'll get a runtime error maximum recursion depth exceeded. If you do, see the teacher's notes for a possible solution. Now let's try running our quicksort program against the 10,000.txt file. Python quicksort.py numbers 10,000.txt. There we go, and it seems pretty fast. But how fast exactly? Let's run it with the time command to see how long it takes. Time python quicksort.py numbers 10,000.txt. Remember, we need to ignore the real result and add the user and sys results. It took less than a second of CPU time to sort 10,000 numbers with quicksort. Remember that selection sort took about 13 seconds. That's a pretty substantial improvement. And with 1,000,000 numbers, selection sort took so long that it never even finished successfully. Let's see if quicksort performs any better. Time python quicksort.py numbers 1,000,000.txt. Not only did Quicksort sort a million numbers successfully, it only took about 11 seconds of CPU time. Quicksort is clearly much faster than selection sort. How much faster? That's something we'll discuss in a later video. What we've shown you here is just one way to implement Quicksort. Although the basic algorithm is always the same, the details can vary, like how you pick the pivot. See the teacher's notes for more details. Let's review another sorting algorithm, merge sort, so that we can compare it with Quicksort. Merge sort is already covered elsewhere on the site, so we won't go into as much detail about it, but we'll have more info in the teacher's notes if you want it. Both Quicksort and merge sort are recursive. The difference between them is in the sorting mechanism itself. Whereas Quicksort sorts a list into two sublists that are less than or greater than a pivot value, merge sort simply splits the list in half recursively, and then sorts the halves as it merges them back together. That's why it's called merge sort. You may recognize this code at the top by now. It just loads a file full of numbers into a list. Let's define a recursive merge sort function. As usual, it'll take the list or sublist that we want it to sort. Our base case is the same as with Quicksort. If the list has 0 or 1 values, there's nothing to sort, so we return it as is. If we didn't return, it means we're in the recursive case, so first we need to split the list in half. We need to know the index we should split on, so we get the length of the list and divide it by 2. So for example, if there are 8 items in the list, we'll want an index of 4. But what if there were an odd number of items in the list, like 7? We can't have an index of 3.5, so we'll need to round down in that case. Since we're working in Python currently, we can take advantage of a special Python operator that divides and rounds the result down, the floor division operator. It consists of a double slash. Now we'll use the Python slice syntax to get the left half of the list. We'll pass that list to a recursive call to the merge sort function. We'll also use slice syntax to get the right half of the list, and pass that to merge sort as well. Now we need to merge the two halves together and sort them as we do it. We'll create a list to hold the sorted values. And now we get to the complicated part, merging the two halves together and sorting them as we do it. We'll be moving from left to right through the left half of the list, copying values over to the sorted values list as we go. This left index variable will help us keep track of our position. At the same time, we'll also be moving from left to right through the right half of the list and copying values over, so we need a separate right index variable to track that position as well. We'll keep looping until we've processed all of the values in both halves of the list. We're looking to copy over the lowest values first, so first we test whether the current value on the left side is less than the value on the right side. If the left side value is less, that's what we'll copy over to the sorted list. And then we'll move to the next value in the left half of the list. Otherwise, the current value from the right half must have been lower. So we'll copy that value to the sorted list instead. And then we'll move to the next value in the right half of the list. That ends the loop. At this point, one of the two unsorted halves still has a value remaining, and the other is empty. We won't waste time checking which is which. We'll just copy the remainder of both lists over to the sorted list. The one with the value left will add that value, and the empty one will add nothing. All the numbers from both halves should now be copied to the sorted list, so we can return it. Finally, we need to kick the whole process off. We'll call the merge sort function with the list of numbers we loaded and print the result. Let's save this. And we'll try it out on our file with 8 numbers. Python mergesort.py numbers 8.txt. And it prints out the sorted list. But again, this seems pretty magical. Let's add some print statements to get some insight into what it's doing. First, we'll print the unsorted list so we can refer to it. We'll add a print statement right before we call the merge sort function for the first time. Then we'll add another print statement within the merge sort function, right after the recursive calls. This will show us the sorted left half and right half that it's returning. Again, don't worry about the fancy Python formatting string. It just keeps the values neatly aligned. Let me resize my console, clear the screen, and then we'll try running this again. What we're seeing are the values being returned from the recursive merge sort function calls, not the original calls to merge sort. So what you see here is after we reach the base case with a list that's only one item in length, and the recursive calls start returning. The original list gets split into two unsorted halves, 4, 6, 3, and 2, and 9, 7, 3, and 5. The first half gets split in half again, 4 and 6, and 3 and 2. And each of those halves is halved again into single-element lists. There's nothing to sort in the single-element list, so they're returned from the merge sort function as is. Those single-element lists get merged into two sublists and sorted as they do so. The 4 and 6 sublist looks the same after sorting as it did before sorting, but the 3 and the 2 get sorted as they're combined into a sublist. The new order is 2, 3. The order is shifted again when those two sublists get combined back into a single list, 2, 3, 4, 6. Then we recursively sort the right half of the original list, 9, 7, 3, 5. It gets split in half again, 9, 7, and 3, 5. And each of those halves get broken into single-element lists. There's nothing to sort there, so the single-element lists are returned as is. The first two are sorted as they're merged, 7, 9, and so are the second, 3, 5. And then those two sublists get sorted as they're combined into another sublist, 3, 5, 7, 9. And finally, everything is sorted as it's merged back into the full sorted list, 2, 3, 3, 4, 5, 6, 7, 9. That's how merge sort works on a list of 8 numbers. Let's see if it works on a bigger list. First, I'll remove the two print statements so we don't get an overwhelming amount of debug output. Then I'll run it on a list of 10,000 items. Python mergesort.py numbers 10,000.txt. Not only did it work, it was pretty fast. But which is faster, merge sort or quicksort? We'll look at that next. I've removed the call to print that displays the sorted list at the end of our selection sort, quicksort, and merge sort scripts. That way it'll still run the sort, but the output won't get in the way of our comparing runtimes. Let's try running each of these scripts and see how long it takes. Time, Python, selection sort, we'll do that one first, numbers 10,000.txt. We combine the user and sys results, and that gives us about 6 seconds. Now let's try quicksort, time, Python, quicksort.py, numbers 10,000.txt. Much faster, less than a second. And finally, time, Python, mergesort.py, numbers 10,000.txt. A little longer, but far less than a second. So even on a list with just 10,000 numbers, selection sort takes many times as long as quicksort and merge sort. And remember, I ran the selection sort script on a file with 1,000,000 numbers, and it took so long that my workspace timed out before it completed. It looks like selection sort is out of the running as a viable sorting algorithm. It may be easy to understand and implement, but it's just too slow to handle the huge datasets that are out in the real world. Now let's try quicksort and merge sort on our file with 1,000,000 numbers and see how they compare there. Time, Python, quicksort.py, numbers 1,000,000.txt. Looks like it took about 11 seconds of CPU time. Now let's try merge sort. Time, Python, mergesort.py, numbers 1,000,000.txt. That took about 15 seconds of CPU time. It looks like quicksort is marginally faster than merge sort on this sample data. We had to learn a lot of details for each algorithm we've covered in this course. Developers who need to implement their own algorithms often need to choose an algorithm for each and every problem they need to solve, and they often need to discuss their decisions with other developers. Can you imagine needing to describe all the algorithms in this same level of detail all the time? You'd spend all your time in meetings rather than programming. That's why Big O notation was created, as a way of quickly describing how an algorithm performs as the dataset it's working on increases in size. Big O notation lets you quickly compare several algorithms to choose the best one for your problem. The algorithms we've discussed in this course are very well known. Some job interviewers are going to expect you to know their Big O runtimes, so let's look at them. Remember that the n in Big O notation refers to the number of elements you're operating on. With selection sort, you need to check each item in the list to see if it's the lowest, so you can move it over to the sorted list. So that's n operations. Suppose you're doing selection sort on a list of 5 items. N in this case would be 5, so that's 5 operations before you can move an item to the sorted list. But with selection sort, you have to loop over the entire list for each item you want to move. There are 5 items in the list, and you have to do 5 comparisons to move each one, so it's more like 5 times 5 operations. Or if we replace 5 with n, it's n times n, or n squared. But wait, you might say, half of that 5x5 grid of operations is missing because we're testing one fewer item in the unsorted list with each pass, so isn't it more like 1/2 times n times n? And this is true. We're not doing a full n squared operations. But remember, in Big O notation, as the value of n gets really big, constants like 1/2 become insignificant, and so we discard them. The Big O runtime of selection sort is widely recognized as being O n squared. Quicksort requires one operation for each element of the list it's sorting. It needs to select a pivot first, and then it needs to sort elements into lists that are less than or greater than the pivot. So that's n operations. To put that another way, if you have a list of 8 items, then n is 8, so it will take 8 operations to split the list around the pivot. But of course, the list isn't sorted after splitting it around the pivot just once. You have to repeat those 8 operations several times. In the best case, you'll pick a pivot that's right in the middle of the list, so that you're dividing the list exactly in half. Then you keep dividing the list in half until you have a list with a length of 1. The number of times you need to divide n in half until you reach 1 is expressed as log n. So you need to repeat n sorting operations log n times. That leaves us with the best case runtime for quicksort of O n log n. But that's the best case. What about the worst case? Well, if you pick the wrong pivot, you won't be dividing the list exactly in half. If you pick a really bad pivot, the next recursive call to quicksort will only reduce the list length by 1. Since our quicksort function simply picks the first item to use as a pivot, we can make it pick the worst possible pivot repeatedly, simply by giving it a list that's sorted in reverse order. If we pick the worst possible pivot every time, we'll have to split the list once for every item it contains, and then do n sorting operations on it. You already know another sorting algorithm that only manages to reduce the list by 1 element with each pass: selection sort. Selection sort has a runtime of O n squared, and in the worst case, that's the runtime for quicksort as well. So which do we consider when trying to decide whether to use quicksort, the best case or the worst case? Well, as long as your implementation doesn't just pick the first item as a pivot, which we did so we could demonstrate this issue, it turns out that on average, quicksort performs closer to the best case. Many quicksort implementations accomplish this simply by picking a pivot at random on each recursive loop. Here we are sorting our reverse sorted data again, but this time we pick pivots at random, which reduces the number of recursive operations needed. Sure, random pivots sometimes give you the best case, and sometimes you'll randomly get the worst case, but it all averages out over multiple calls to the quicksort function. Now with merge sort, there's no pivot to pick. Your list of n items always gets divided in half log n times. That means merge sort always has a big O runtime of O n log n. Contrast that with quicksort, which only has a runtime of O n log n in the best case. In the worst case, quicksort's runtime is O n squared. And yet, out in the real world, quicksort is more commonly used than merge sort. Now why is that if quicksort's big O runtime can sometimes be worse than merge sort's? This is one of those situations where big O notation doesn't tell you the whole story. All Big O can tell you is the number of times an operation is performed. It doesn't describe how long that operation takes. And the operation merge sort performs repeatedly takes longer than the operation quicksort performs repeatedly. Big O is a useful tool for quickly describing how the runtime of an algorithm increases as the dataset it's operating on gets really big. But you can't always choose between two algorithms based just on their Big O runtimes. Sometimes there's additional info you need to know about an algorithm to make a good decision. Now that we can sort a list of items, we're well on our way to being able to search a list efficiently as well. We'll look at how to do that in the next stage. Now that we've covered sorting algorithms, the groundwork has been laid to talk about searching algorithms. If you need to search through an unsorted list of items, binary search isn't an option, because you have no idea which half of the list contains the item you're looking for. Your only real option is to start at the beginning and compare each item in the list to your target value, one at a time, until you find the value you're looking for. This algorithm is called linear search, or sequential search, because the search proceeds in a straight line, or sequence. Even though linear search is inefficient, searching for just one name will happen so fast that we won't be able to tell anything useful about the algorithm's runtime. So let's suppose we had 100 different names, and that we needed to know where they appear in a list of unsorted names. Here's some code that demonstrates. As usual, this code at the top isn't relevant to the search algorithm. It's just like the code that loaded a list of numbers from a file in the previous stage, but this code calls a different function, loadStrings, that loads a list of strings in. If you want the loadStrings Python code, we'll have it for you in the teacher's notes. Here's a separate hard-coded list containing the 100 names we're going to search for. We'll loop through each name in this list and pass it to our search function to get the index within the full list where it appears. Now let's implement the search function. Compared to the sorting algorithms, this is going to be short. The index of item function takes the Python list you want to search through and a single target value you want to search for. Now we need to loop over each item in the list. The range function gives us a range of numbers from its first argument up to, but not including, its second argument. So if our list had a length of 5, this would loop over the indexes 0 through 4. We test whether the list item at the current index matches our target. If it does, then we return the index of the current item. This will exit the index of item function without looping over the remaining items in the list. If we reach the end of the loop without finding the target value, that means it wasn't in the list. So instead of returning an index, we return the special Python value none, which indicates the absence of a value. Other languages have similar values like nil or null, but if yours doesn't, you might have to return a value that would otherwise be impossible, like an index of -1. Now let's call our new search function. We start by looping over the list of 100 values we're looking for. We're using the values themselves this time, not their indexes within the list, so there's no need to mess with Python's range function. Here's the actual call to the index of item function. We pass it the full list of names that we loaded from the file, plus the name we want to search for within that list. Then we store the index it returns in a variable. And lastly, we print the index we get back from the index of item function. Let's save this and go to our console and see if it works. Python linearsearch.py names unsorted.txt. And it'll print out the list of indexes for each name. I actually set it up so that the last two items in the list of names we're going to search for corresponded to the first and last name within the file. So if we open up our unsorted.txt file, we'll see Mary Rosenberger is the first name and Alonso Viviano is the last name. And those are the last two values in our list of names we're searching for. So it returned an index of 0 for that second to last name, and you can see that name here on line 1 of the file. The line numbering starts at 1, and the Python list indexes start at 0, so that makes sense. And for the last name, it returned an index of 109873, and you can see that name here on line 109874. So we can see that it's returning the correct indexes. But right now, we're just searching for 100 different names in a list of 100,000 names. In the real world, we're going to be looking for many more names than that, within much bigger lists than that. Can we do this any faster? Yes, but we'll need to use the binary search algorithm. And for that to work, we need to sort our list of strings. We'll do that in the next video. Before we can use the binary search algorithm on our list of names, we need to sort it. Let's do that now. We need to load our unsorted list of names from a file, sort it, and write the sorted names back out to a new file. Again, this code at the top just loads a file full of strings into a list. We'll use our quicksort method to sort the list of names. Its code is completely unchanged from when you saw it in the previous stage. We just call our quicksort function on the list of names loaded from the file, and save the list to a variable. Then we loop through each name in the sorted list, and we print that name. That's all there is to it. Let's save this script and try running it. Python quicksort strings.py, and we'll pass it the names unsorted.txt file. Let me resize the console window here a little bit. That prints the sorted list of names out to the terminal, but we need it in a file. So we'll do what's called a redirect of the program's output. We'll run the same command as before, but at the end we'll put a greater than sign, followed by the path to a file that we want the program output written to, names sorted.txt. Redirecting works not only on Linux-based systems like workspaces, but also on Macs and even on Windows machines. You just need to be careful because if you redirect to an existing file, its contents will be overwritten without asking you. Let me refresh the list of files in the sidebar. And you'll see that we now have a new sorted.txt file in the names directory. It's the same number of lines as the unsorted.txt file, but all the names are sorted now. Now we can load this file of sorted names into a list, and we'll be able to use that list with the binary search algorithm. We'll see how to do that next. Now that we have our list of names sorted, we can use the binary search algorithm on it. Let's see if we can use it to speed up our search for the indexes of 100 names. Binary search keeps narrowing down the list until it has the value it's looking for. It's faster than linear search because it discards half the potential matches each time. Our code here at the top of our binary search script is unchanged from the previous scripts. We just call the loadStrings function to load our 100,000 sorted names from a file. Here we've hard-coded the list of 100 names we're going to search for again. It's identical to the list from the linear search script, except that I've again changed the last two names to correspond to the names on the first and last lines of the file we'll be loading. Now let's write the function that will implement our binary search algorithm. Like the linear search function before, it'll take two arguments. The first is the list we're going to search through, and the second is the target value we'll be searching for. Again, the binary search function will return the index it found the value at, or the special value none if it wasn't found. Binary search is faster than linear search because it discards half the values it has to search through each time. To do this, it needs to keep track of a range that it still needs to search through. To start, that range is going to include the full list. The first variable will track the lowest index in the range we're searching. To start, it's going to be 0, the first index in the full list. Likewise, the last variable will track the highest index in the range we're searching. To start, we'll set it to the highest index in the full list. If the first and last variables are equal, then it means the size of the search range has shrunk to 0 and there is no match. Until that happens, though, we'll keep looping to continue the search. We want to divide the list of potential matches in half each time. To do that, we need to check the value that's in the middle of the range we're searching in. We add the indexes in the first and last variables, then divide by 2 to get their average. We might get a fractional number, which can't be used as a list index, so we also round down using Python's /floor division operator. All this will give us the index of the list element that's the midpoint of the range we're searching. We store that in the midpoint variable. Whoops, looks like my indentation got mixed up there. Let me fix that real quick. There we go. Now we test whether the list element at the midpoint matches the target value. If it does, we return the midpoint index without looping any further. Our search is complete. Otherwise, if the midpoint element's value is less than the target value, then we know that our target value can't be at the midpoint or any index prior to that, so we move the new start of our search range to just after the old midpoint. Otherwise, the midpoint element's value must have been greater than the target value. We know that our target value can't be at the midpoint or any index after that, so we move the new end of our search range to just before the old midpoint. By unindenting here, we mark the end of the loop. If the loop completes, it means the search range shrank to nothing without our finding a match, and that means there's no matching value in the list. So we return the special Python value none to indicate this. Lastly, just as we did in our linear search script, we need to search for each of the 100 names. We loop over each name in our hard-coded list, and we call the binary search function with the sorted list of names we're going to load from the file, and the current name we're searching for. We store the returned list index in the index variable. And finally, we print that variable. Let's save this and go to our console and try running it. Python binary search.py, and it's important to give it the name of the sorted file. If it loads the unsorted file, the binary search won't work. So, names sorted.txt. Again, it prints out the list of indexes for each name. I once again set it up so the last two items in the list of names we're going to search for corresponded to the first and last name in the file. So it returned an index of 0 for the second to last name. And you can see that name. Here's the second to last name, Aaron Augustine. You can see that name here on line 1 of the file. And for the last name, it returned an index of 109873. And you can see that name here on line 109874. Let's check the third to last name for good measure. It looks like an index of 97022 was printed for that name, Stephen Darris. Let's search for Stephen Darris within the file. And here it is on line 97023. Remember that line numbers start on 1 instead of 0, so this actually matches up with the printed list index of 97022. It looks like our binary search script is working correctly. Let's try our linear search and binary search scripts out with the time command and see how they compare. I've commented out the lines that print the indexes of matches in the two scripts. That way they'll still call their respective search functions with the 100 names we're searching for, but they won't actually print the indexes out, so we won't have a bunch of output obscuring the results of the time command. First, let's try the linear search script. Time, Python, linear search.py, names, and we can just use the unsorted list of names for linear search. Remember, we want to ignore the real result and add the user and sys results together. It looks like it took about 0.9 seconds for linear search to find the 100 names in a list of 100,000. Now let's try timing the binary search script. Time, Python, binary search.py, names, and for this one we need to use the sorted list of names. Looks like that took around a quarter second, so less than half as long. Bear in mind that part of this time is spent loading the file of names into a list. The difference between linear search and binary search will be even more pronounced as you search through bigger lists or search for more items. Let's wrap up the course by looking at the Big O runtimes for linear search and binary search. These are going to be much simpler to calculate than the sorting algorithms were. For linear search, you need to do one comparison to the target value for each item in the list. Again, theoretically, we could find the target value before searching the whole list, but Big O notation is only concerned with the worst case, where we have to search the entire list. So for a list of 8 items, that means 8 operations. The Big O runtime for linear search is ON, where n is the number of items we're searching through. This is also known as linear time, because when the number of items and number of operations are compared on a graph, the result is a straight line. Linear search looks pretty good until you compare it to binary search. For binary search, the number of items you have to search through, and therefore the number of operations, is cut in half with each comparison. Remember, the number of times you can divide n by 2 until you reach 1 is expressed as log n. So the runtime of binary search in Big O notation is O log n. Even for very large values of n, that is, very large lists you have to search through, the number of operations needed to search is very small. Binary search is a very fast, efficient algorithm. That's our tour of sorting and searching algorithms. Be sure to check the teacher's notes for opportunities to learn more. Thanks for watching.